Well, good morning. I just want to say how much I enjoyed yesterday, and I really particularly enjoyed the panel discussion. I could have listened for about another 3 hours there. I'll be talking about how we use the shelf fleet data, and the main point of the talk is the dialogue that's really developed, and the way that I've learned about the fishing practices and the fishing outcomes and their relation to the oceanography, and vice versa. I think the community has learned a little bit about shelf break processes. I'll give a quick background on the regional circulation. And my own research specialty is shelf break processes there. And I've been doing that since 1984. And I do remember an NSF reviewer that in a review that actually turned down the proposal said that Gorkwitz has been studying shelf break processes since early childhood. And I just want to correct that. It really was a little bit later than that. I'll briefly review the shelf fleet. I know Noel did a really nice job yesterday covering things. But I really want to talk about the oceanography. And in particular, the Northeast is being impacted by changes in both the Gulf Stream and the jet stream. And while early in my career I was very, very concerned about the local conditions, what we're finding is basically global scale dynamics are really affecting things in our local area. It makes it exciting in terms of the science, but it also means that we're seeing differences in processes in particular that I really want to highlight. And those processes are intrusions coming across the continental shelf. And one of the things we've been able to do is train people to see the signatures of the processes in the individual profiles that they're collecting so that they can make better decisions. And then finally, I have one slide moving forward that's pretty similar to a lot of the other ones there. So in terms of the regional circulation here, there's two important current systems, the Gulf Stream, which lots of people have heard about, and that's a wide, strong western boundary current that carries a lot of heat northward. But the current system that I've studied is the shelf break jet, and that actually comes down from Labrador there. It's part of a very large current system. And the main way that the Gulf Stream influences the continental shelf and the shelf break region is by shedding warm core rings. And those are large clockwise eddies. They can be 60 nautical miles in diameter there. And as the community knows better than I do, you get streamers of shelf water coming out, and that can be very productive in these streamers right there. One of the fascinating things about the shelf break jet is that the dynamics are very nonlinear, and it creates meanders and it pinches off eddies of shelf water that actually go out into the deep ocean. And that's really been the focus of my research is how waters from the continental shelf get offshore and how waters from the continental slope get onshore. And we've seen big changes in the last 5 years. So this is a climatology right here. And this is for the summertime. This is temperature. This is depth right here. And this is cross-shelf distance. And these are ice attacks of velocity right here. So the shelf break jet is relatively narrow there, particularly with regard to the Gulf Stream. But the currents can be very strong, and there can be very strong lateral shear. I remember being on the bridge of a research vessel and the captain saying, "Oh, the ship just moved 50 yards sideways." And it's like, oh yeah, we're in the edge of the jet. Since this is the summer, we've got the summer warming right there and the thermocline. And this is a very important water mass, the cold pool right here. And by definition, that's under 50 degrees Fahrenheit right there. That's been warming up there. In terms of the salinity, the continental shelf is always fresher there, and there's about a 2 part per thousand practical salinity unit difference with the deep ocean. The gradients are usually coinciding with each other there. Okay, so this cartoon pretty much summarizes my entire career, actually, so I'm very careful not to delete it on my computer. And so this is the front right here schematically. This is the jet. The jet is very surface trapped, actually. And one of the things that's really important about the front is there's persistent upwelling right here. And this feeds right into the heart of the jet there. And it's a big distinction with the West Coast because it's just the mean flow that drives this upwelling there. You don't need the winds, actually. And that makes the shelf break light up. I remember one of Anna's figures there from the cooperative research showed all that activity along the shelf break all the way down to Cape Hatteras. Now, the warm core rings actually have a pretty large vertical extent, much deeper than the edge of the continental shelf, 300 feet right here. So they don't get onto the continental shelf. But as we'll see, they drive intrusions that actually can get across the continental shelf. And those dynamics are very complicated. We're studying them, but it is a tricky problem. We just did 2 cruises with what are called mid-depth salinity maximum intrusions. I'll explain what those are like. But we actually used shelf fleet profiles before the cruise to identify where these intrusions were. And then also, the first process I'll talk about are actually bottom intrusions, which turn out to be very important and get surprisingly far across the continental shelf. Next one, Cooper. Okay, so just in case anyone wasn't here yesterday, a quick review on the shelf fleet. We've been collecting data since 2014. We were originally funded by the MacArthur Foundation. That was the first grant to Hui in over 30 years, actually. And then the Van Buren Charitable Foundation, which normally funds historical restoration in Newport and healthcare in Rhode Island. So that I used my best salesmanship skills with that foundation. Again, as Noel pointed out yesterday, we have 6 different zones right here. These were all the profiles as of last February 2022. And one interesting thing you'll notice is there's a lot of fishing along this buried river channel right here. And I will return to that as a science issue a little bit later there. That goes past Cox's Ledge. Next one. And just key personnel. Anna was just instrumental in setting it up. Aubrey and Noel have been doing all the interactions and figuring out schedules, when to get the CTDs, listening to all the problems. Dave and Susan have provided great support, and of course, Dave has that money thing going on with me. And Frank Barr, who is actually retired now, we're having his retirement party on Friday. He is the Hui engineer who's been processing the data and providing all the technical support. And of course, the fishers and the fishing vessels. The interactions, for me personally, have just been incredible. Next slide. Okay, and then here's some pictures from the 2022 fleet participants there. Next slide. And so the key elements, we've been shooting for every 2 weeks. In practical terms, it's the 4 most onshore zones. Zone 5 is in the middle of the Pioneer Array, that large ocean observatory, but that was pulled out in November there. We're using the RBR Concerto. The wireless connection is very important because people can actually make fishing decisions about that particular location. And again, this whole thing about interpreting what the profile is saying is very important. These update meetings have just been unbelievable. I usually prepare, what would be in an academic setting, 20 minutes worth of material, and the discussions usually go between 2 and 3 hours. Our last one was on December 8th, and it was just incredible. The inputs were just absolutely wonderful. Now, we're really starting to get this data used in different formal management settings. And the most important one so far was the scientific working group report for the stock assessment for short fin squid. And Sarah Solois was the lead author on that. And partially as a result of this input, the quota was increased by 21% for this year. So it's actually had a demonstrable impact in management. And then I was involved in 2 experiments, something called Task Force Ocean, to work on acoustic propagation and submarine tactics there in May of 2021. That experiment did not collect data over the continental shelf. They relied entirely on shelf fleet profiles, and Cooper was also involved with that, with some profiles further offshore. And then also 2 cruises to study the mid-depth salinity maximum. And I'll talk about that at the very end. Next slide. Okay, and so this is the whole time series right here. Again, as Noel showed yesterday, the different zones with the different profiles. This is salinity first. Noel highlighted 2021 as a time period where there was a lot going on. The shelf break front actually moved inshore for 5 months. But you can see that the largest signals in the salinity are when the warm core rings are nearby. And because we have the Pioneer Array data from 2014 until November 2022, we can actually identify the warm core rings offshore. Also, a PhD student at SMAST, Adrian Silver, has actually tracked the trajectories of all warm core rings over the last 10 years. So we'll be combining this data on the intrusions with that data as well. Next slide. And then these are the temperature fields. Again, you can see the development of the seasonal thermocline in each year. There's a manuscript submitted about 2 weeks ago by a grad student here that actually quantifies the breakdown of the stratification every fall for 7 years from the Pioneer Array. And so we'll combine this data with the Pioneer Array down the road. Next slide. Okay, and now here's the large-scale framework for the changes that are going on. So in January 2013, we had a workshop on the shelf break ecosystem because we're trying to motivate a National Ocean Partners program. And Fred Matera gave the first talk from CFRF, and he had a list of 10 different observations from the fishing community. And number 1 was more Gulf Stream water on the continental shelf. And that was the first I'd heard of it. And I can't tell you, that led to like 5 years of research here at Woods Hole. And the first paper that came out that really reflected this was by Magdalena Andres in my department, a physical oceanographer. By the way, her son is a commercial fisherman, Ian, there. And what she noted was from the satellite altimeter, which measures sea surface height, that back in the mid-1990s, the Gulf Stream was very stable and very straight. This line right here marks a height contour in the north wall of the Gulf Stream where there's a big sea surface gradient. And so the large meanders didn't start till like 55 degrees west. But as time went on, actually, the Gulf Stream became more unstable. And we can see in 2014, there were much larger meanders and they began much further west. So the north wall of the Gulf Stream is now occasionally actually hitting the shelf break. And the first time I learned about that was on December 16th, 2011, in a meeting about the Pioneer Array. I was told we've got 5-knot currents out at the shelf break. It's 72 degrees and it's December 16th. What the hell is going on, Mr. Oceanographer? So that was my only Google oceanography project. I got online, found drifters that were going up, the Jim Manning deployed, of course. And it turns out the drifters followed the north wall of the Gulf Stream, hit the shelf break south of Georges Bank. And that was the first time I realized, the Gulf Stream meanders were just really, really getting more active there. So the second thing, this was published in 2016. In 2017, Avijit Gangopillai had at SMAST had a master's student who was looking for a topic, and I said, the Gulf Stream is getting kind of wacky here, just to use the technical term. And why don't your student update a census of the warm core rings? So he did it. This led to 4 different theses, and dramatically, from the Jennifer Clark analysis charts, there was a big shift in the year 2000 in the number of warm core rings, going from 18 per year to 32 per year. I was surprised. People have been running all sorts of computer models and things like that, but we picked that up from the charts there. And so Adrienne Silver has worked on this as part of her PhD thesis. If you take that difference in the number of warm core rings, 7% of the heat from the Gulf Stream that was going northward prior to 2000 is now going into the continental slope. So that's one of the reasons I think the species are changing so much there. Okay, so now the atmosphere. I was in a hotel room with jet lag in Taipei, Taiwan, oddly enough, on an economics website, and they had a link to a short video by Jennifer Francis, who's a meteorologist here in Woods Hole at the Woodwell Center, and it was about the slowing down of the jet stream, actually. So she works on warming of the atmosphere in the Arctic, but she's connected that to unusual weather patterns at mid-latitudes. She's very popular with the media, I should add. In May of 2012, we were doing a cruise down near Cape Hatteras, and the water temperatures were 11 degrees Fahrenheit warmer than I expected. And I knew that there were issues with climate change, but that was the first time it just really hit me right in the face. And we were looking for bluefish and butterfish for an acoustics project. We couldn't find them. We had all warm water species there. So I came back, and my postdoc, Ka Chen, had just started. So he ended up looking at the winter of 2011, 2012, and it turns out that the jet stream in the fall came down south for the winter, bringing the cold air 6 weeks later than usual. So 50% of the heat loss from the ocean to the atmosphere just didn't happen there. And that led to temperature anomalies as large as 5 degrees Fahrenheit for 6 months there. And of course, 2012, when there was all the disruption to the lobster and the timing with the processing plants in Canada, it had huge economic impacts. Seabirds were drastically affected. There were a lot of mass die-offs in the Northeast. Next slide. Okay, so now how do we connect the data from the shelf fleet processes to these larger scale changes? It's in the individual profiles, and this is a pretty dramatic one right here, right before Christmas of 2020. And so this is one of the profiles. You go down and look at this in the last 30 feet. The temperature is increasing by about 5 degrees Fahrenheit there, and the salinity is increasing by 1 part per thousand. And look at how sharp that gradient is right there. So in this particular time period, I was procrastinating before writing a proposal. I was looking at the Pioneer Array data, and I saw this intrusion. It was like, holy moly, something's going on. 10 minutes later, I got a phone message from Aubrey saying, and she hadn't checked her email. She said, Glenn, what's going on? The guys at the dock are asking me, is there a bottom intrusion out there? So I knew from the data and from all these interactions that the bottom fishing outcomes are strongly affected when these bottom intrusions happen. And they knew from their fishing outcomes, wow, this must be a shelf break exchange process, bottom intrusions. So I just thought that really showed the value of those 7 years of interactions up to that point. I think both sides have really learned. And in response to that question about trigger events there in the panel discussion yesterday, we really need both sides talking to each other to figure out these triggers. Next slide. Okay, so the profiles in 2017 led directly to basic research. And Mike Marchetti actually sent a picture of a Gulf Stream flounder to Anna Mercer. She passed it on to me. And he was asking, why is this warm water fish up near Block Island in January? So we looked at the shelf fleet profiles. There was a bottom intrusion then. We ended up writing 2 papers about it there. But just in the past year, Ka Chen, my colleague, who's a numerical modeler, did a hindcast simulation of January 2017. And the model shows this beautiful bottom intrusion going on shore. In the data, it reached all the way up to Block Island. It didn't quite get that far in the model. It probably has something to do with the bottom friction being a little bit too high there. But this paper was published late in 2021 there. And there's all sorts of analysis of the momentum balances and things. These presumably bring nutrients on shore too. Next slide. And then just a final comment about these bottom intrusions. One of the things I found very interesting was the little depression in that buried river valley that runs up past Cox's Ledge. The intrusion in 2017 seemed to follow that. So the bathymetry may be very, very, very important. And I was telling my old roommate from graduate school about this, who's a geochemist. And he said, well, of course, you've got all that organic carbon there in the old buried river channel from the Ice Age. You know, of course, that's going to be you know, some kind of aggregation area there. So I thought that was an interesting insight. I certainly want to talk to biogeochemists more about that. Next. Okay. So I mentioned mid-depth salinity maximum intrusions. And this is a schematic here. This is a real profile, but it's basically to define the terms. This is salinity right here. This is depth. This profile was around 240 feet, something like that. And what's been seen and known since the 1930s is that you can get these maximum in salinity at mid-depth. They can be higher than any other value in the water column. They have to have come in from offshore there. And so this is another process, you know, that we've talked about in the Shelf Fleet oceanographic updates. Next slide. One of my first things to do when the pandemic hit, when I was confined to my daughter's bedroom, was actually, in that blissful month before Zoom was discovered, was analyze the Shelf Fleet data. And so I had data from 2015 to 2019. And this is a plot here, the kind of greenish here are profiles with salinity maximum intrusions. You can see these are up, you know, right by Cox's Ledge here. They're coming in from this region right here. They're going all the way across the continental shelf there. And then the black dots are the profiles without. They only occur during the stratified part of the season. They're normally centered right in the maximum temperature gradient. But this was a shock because normally in the literature, there's a very nice paper by Steve Lentz that showed they normally only went about 20 miles shoreward from here. So normally they would only have gone up to there, up to like 1998. But we're getting these intrusions going much further onshore. Next slide. And so this was the plot, when I first plotted it up, that really kind of floored me. Was I took the fraction of the profiles for each of the months. So the red is for the 5 years average together for the different months of the year. And the blue is from the climatology from Steve Lentz that used data from 1960 to 1998. So his maximum was in August and September here, about 25% of the profiles. But you can see almost 50% of the profiles from 2015 to 2019 actually had these intrusions there. These are presumably carrying biogeochemical signatures with it. I'm just really excited to talk to people about some of these implications for cross-shelf fluxes there. You can also see how, you know, it's really the late summer when it's most stratified when these intrusions are the strongest. Next slide. The other thing I think that's really fascinating biogeochemically is many of the profiles now have multiple intrusions in them. And this didn't used to be the case. There's no mention in the Lentz paper, and you know, certainly I haven't looked through all 10,000 of his profiles. But this is very common now. 10% of the Shelf Fleet profiles, but 20% of the Ecomon profiles over 30 years that Paula Frattantoni examined have these multiple layers to them. So, you know, I have a couple questions. You know, are zooplankton now going to different layers? How is this affecting whale feeding? Is there less concentration in each individual layer? If there's 4 different layers? I was out on one cruise in 2016 where we had the EK80 system, which is multi-frequency. And in that one particular cruise, we could see that small zooplankton were indeed in multiple layers. And with the low frequency, where you can actually see the trajectories of the fish, they were actually going between layers and feeding on different layers there, which, you know, gets into the whole predator-prey interaction stuff. Okay, next slide. So moving forward, I am just so excited about this meeting because we really need to add a broader suite of sensors to the CTDs in the fleet here. We need to expand the shell fleet to a regional network, and I think this workshop is a great step in that direction. We have really not had any funding for analysis of the data. Everything has been done as part of another project that we're doing there. And one of the first things I would want to do was expand the visualization and the web survey. And I was really inspired by Tracy's talk yesterday about using the GIS system, and that looked very nice and straightforward and easy to see. That's something I would love to do in conjunction with the fishing industry to see what kind of visualization is the best. The fishing community is very busy. My heart always sinks when we're going to do a shell fleet update meeting and it's good weather, because I know most of the guys are out fishing. I'm always praying for bad weather there. But one of the things, you know, I've been thinking about is, can we do 8 to 10 minute little videos there? And then also, you know, I need to talk to Dave about maybe, you know, having a blog or something like that where we pull in some of the different sources. It's something I've been meaning to do for 7 years, but I'm a procrastinator. And really, another thing that I feel very, very deeply about is we really need to build the trust and interest with young scientists to get them to see how important the interactions with the fishing community are. And that's something I always try and include young scientists in as many of the interactions as I possibly can. And I do entice them. I'm pretty shameless because I do say, you're going to find out where the best seafood restaurants are there. And that's something you can use professionally for a long time. Last slide. So I mentioned the salinity intrusion project there. So in September 2022, we went out, Susan was out there with us, tweeting during the whole cruise. And there was a worm core ring out there, and there was a huge intrusion moving on shore. So we were able to identify, even from the sea surface temperature, where that subsurface feature was, which I was really pleased about that. There. We also put out a long-range AUV from Amy Kakulia's Cybotics group here at Woods Hole that did this pattern right here. So the big shocker for me was the velocities, because there was an onshore northwest flow of 25 centimeters a second, which is nearly half a knot. And so, you know, one of our big questions was, is this affecting ilex squid? Is the burstiness of their appearance related to these type of intrusions? And Anna, being the usual go-getter that she is, chartered the FV Durston to be out there. So we actually gave them coordinates of where the salinity maximum intrusion was. It was about 6 miles wide. And they did 8 different tows. So they have all the statistics for both the weights and the lengths. And we'll be using that for ilex research moving forward. So with that, I'll stop.
Hello. Yeah. Thank you very much, Glenn. That was fascinating. Always learn so much, you know, every time you talk, and it's, we've got time for just a couple questions. Is anybody, I'm sure we've got lots of questions. Let me wait till I get the mic over to you.
It's a great speech, Glenn. Thank you. What's going to happen if you mix the thermoclines? When I fished down there, I was down there for 20-odd years in zone 1, 2, and 3. And some days we could actually see the thermoclines in the sounders.
Yeah. Oh, yeah, absolutely.
Yeah. So what happens when you mix those thermoclines up? If something...
That's really interesting. And, you know, one of the things that my student Lucas Lobert has found is that mixing occurs over a big time span from year to year. So it's like a 2-month difference between the earliest time of breakdown to the latest time of breakdown there. You're certainly mixing nutrients up there from what I've heard from all the shelf fleet discussions, the whole fishing situation rearranges itself there. The mixing also affects the strength of the shelf break jet, because you also affect the density gradients, and it's the density gradients that drive that current. And the strength of the current determines the strength of the upwelling. And so I think that there's a lot of subtle things that go on. We are just scratching the surface of the dynamics when that happens. But I think it really reorients the whole system into a different state there. Have you seen that in the fishing? You know, did things move around a lot?
Yeah, I mean, I don't want to go down this path, but you start putting all those windmills out there and those big towers, 60 feet diameter. And you know, I have a pool at home and there's water, cold water, and warm water on the top and cold on the bottom. You put your arm in there and move it. It mixes the water up. I'm concerned what's going to happen to the fishing once you start mixing those thermoclines up.
Yeah, and I know the cold pool is a big issue.
Okay, one more real quick, Hassan.
Okay, we have an online question. What are the other kinds of sensors you'd like to see beyond CTDs?
Oh my goodness. Chlorophyll A fluorometer, oxygen, let's see, DIC, alkalinity, every single sensor we're going to talk about this afternoon.
Let's get Hassan in here. We're only 1 minute late, so.
The question maybe is beyond this audience, but thank you, Glenn. Always good to hear what you say. And we are going to talk about squid now.
Yes.
Another time. But my question is, do you have any idea what triggered that 1995 or that period of shoot, that thing that completely changed that regime?
Yeah, that is a great question.
Sorry,
and, you know, but it gets into the dynamics of the Gulf Stream. And one thing that we're really curious about is how wide the Gulf Stream is and how strong the current is. Because the shear, in other words, if the velocities are faster or if it gets narrower, it should be more unstable. And a VGIT student, Adrian Silver, is actually working on that. And so we're using satellite data to go back 30 years to see if it is getting narrower, if it is getting stronger. That's a great question.
All right. Thank you again very much, Glenn. And next up, we have Jim Manning, who, you know, the godfather of this all, as I like to say, and, you know, personally been a huge mentor for me. So yeah, I'll let you take it away.
Thank you. Now, you might recognize my voice, and I'm running on low batteries this week. But I have enough voltage to get through this talk here, and kind of a not real polished talk. Try to get through quick. I'm just going to make two or three basic points. And one is that they wanted me to asked to talk about existing technology, but I changed that word to evolving because there's no. If I talked about existing, it'd be obsolete next year by the time we get a proposal together. I wanted to just tell a story about how things have evolved over several years that we've been playing with these things. And the other point is that although we try to design a system that's hands-free, and it doesn't go that way. You need lots of people, and that's where the money's. Oh, the numbers are gone here. 1, 2, 3, and 4. Number 4 is the most expensive part. These little sensor pieces are pretty cheap. So I'll go through a couple slides on the probes. What are probes? I mean loggers, instruments, sensors, things that go in the water, deck boxes in the wheelhouse, and transmitters to get the data. I'll emphasize this last one here. So, quick. This is, by the way, the temperature, mostly temperature for EMOLT we're talking about here. We started out the first two with internally recording things. But to go real time, we had to go up an order of magnitude cost to wireless. We started a couple of years with Aquatech, and it's still being used in the study fleet from England, and moved on to Nick's unit in the last 5 or 6 years, and more recent in the last couple of years, the Moana probe. That's good. Go ahead, Cooper.
Okay. Sorry, this thing keeps popping up.
So when we try out these new rigs, we got to test them out and compare them, and we do 2 kinds of tests. One is in an ice bath. Typically annually put them all in ice. Hui has a nice facility here that I've used for several years. But during COVID, I set up in my home a tub with a stirrer and into 7-Eleven to get the ice. They simulated Gulf of Maine season in a couple hours, and just to satisfy myself that they're getting down to the 0.1 degree C that we were striving for, and we were happy to get that from all the tests we've done, both in the bath and at sea, thanks to Mark Phillips, Greenport, and Judith. He's got 3 different sensors on his gear now, and so we can compare. This is one haul over 2 hours for him with the 3 different sensors, all recording a haul average within 0.1 degree. So, but that's important that we keep testing new rigs as they come. All right, next slide. Oh, two quick one that you've already heard. These go on the trawl doors, the dredges, the long lines and jiggers and traps. If anything goes down to the bottom and comes up, we have it. Next slide. And before I leave the topic of probes, sensors, I wanted to make note that we have tried other sensors and experiments over the years. And almost 20 years ago, we gave half a dozen lobstermen some seabird microcats in their traps for several months. And we showed it can work. Trouble is a little mud and biofouling. It makes it, getting in the conductivity cell makes it difficult to handle that data. But I think it can be done, and we'll come back to that in the future, I think, to get the things up off the water. And about 10 years ago, Vitaly Sherman and I put little tilt current meters that Vitaly put together on 50 different lobster traps along the coast. We measured a long trap and cross trap flow. It was fun for several months. The fishermen were curious to see that. And one interesting came of that is that a lot of times the trap was upside down, so there wasn't any current. They were interested to see that. But we couldn't go operational. We just didn't have the funds to do that. And same thing with the weather stations. A couple of weather stations on vessels. Jim Ford out of Newburyport and Mark Phillips, Greenport. We were sending hourly data automatically to the National Weather Service from offshore. When we tried to get some more money from National Weather Service, didn't go. But that can be, that works. And the one experiment that did work, though, was in 2004, we sent some fishermen out with drifters, satellite track surface drifters. And that is operational, still going on. I'll talk about that this afternoon in a flash talk. So getting on to the second part. Next slide, to deck boxes. How do we get thanks to George for this slide here, how do we get to the data back to shore? And how do we display it in the wheelhouse? Next slide. So we started out with a little $35 Raspberry Pi inside this 7-inch screen. And I found this photo in my disk. I was looking, hey, that's interesting. There's 2 weeks here of a trap data, and this is depth here. This is one of Nick's Lowell's probe, detecting this noise here for a couple of days of a storm. Is enough accuracy and enough pressure to at least give us an indication that something's going on here. Storm, yeah, that's a storm that drove that, turned the water over and raised the water temperature by about 10 degrees Fahrenheit in those 2 days. And so the fishermen can see this And they note the average temperature of that trawl, as well as the climatology that's based on decades of Northeast Fisheries Science Center CTD surveys. This climatology here is a 30-year average. So in this particular case, that trawl was 4 degrees warmer than it should be at that time of year in October. So anyway, we have this thing, and we migrate to other deck boxes over the time. And a big acknowledgement to my 2 colleagues here from long term. And this is one reason why this CMO project worked. It's consistent. It's a good thing we don't swap out the people like we swapping out is because they've been with me, and I much appreciate it. Aaron and Juan, they got 2 different types of deck boxes, and this is a more recent one from Nick. Yep. So in addition to the deck box, there's we have to get the GPS a couple different ways. In our rig, we just put a puck up on the window. Nick has one internal to his box. Sometimes we have to use extensions. Every ship is different. Every wheelhouse has to be rigged differently to get it right. So there's a lot of experiments and extending the antennas. Sometimes outside, next slide shows getting to transmitters. So we mount these transmitters. This is to get to the satellite in different places on the upper deck, on the crossbar. Sometimes inside, if it's a wooden wheelhouse, you can sometimes get through that. We can just put it in here. And some of the newer transmitters that we use in these rock blocks seem to work pretty well inside the wheelhouse. So that makes it easy not have to rig it outside. And as Julie and Cooper showed yesterday, there's a new one coming along. This is a lot simpler because you just snap it on the deck someplace and solar powered, and doesn't get in the way in the wheelhouse and everything runs. But that's an option for some boats that don't care. Maybe the captains don't care about seeing something in the wheelhouse. This will go right to the cloud. There's cell connection right now, I think. Yeah. So, sorry, a real quick run through the technology, but I want to get to this. What's next? Big acknowledgement to Nick. I appreciate helping us. Watching, I jury rigging a lot of stuff for many years, and he come along to help us. And I just want to say it's important to have an engineer locally that can come to your kitchen and talk to you. And this is good. Before him, we were dealing with people from England. They wanted us to send the instrument back to England to check something. But Nick's right there. And when we have probe goes wrong, we throw it in his mailbox, put enough down with him. He fixes. I appreciate it. Next. And I appreciate the help from all these various groups. This is very important that if we're going to do this coast-wide, we got to get together with all the other people that are doing similar things all along the coast. Cooper and Jack, for example, up in Portland. Cooper, a revolutionary crusader of this thing around the world, has been great help. I appreciate it. And GMRI, Aaron here, Gio, and others from Study Fleet techs helped us quite a bit. And of course, Aubrey at CFRF and others, and the Shell Fleet connection. Owen has been great. For example, in P-Town, we don't have to drive up to Provincetown. He's got 3 or 4 boats up there, and he's taking care of them. We had a great thing going with the university in China until COVID happened, and I hope to it'd be nice to get that back going. That helped me a lot for a couple of graduate students come here for a year each. I had about 10 of them come, and that's was a big help. And George, originally at the Alliance, fortunately we got him there, didn't come to NOAA. And well, the point is they're switching around now. Everybody's switching. We're all in the same game, and we have to work together. So if I had one slide, and I would show this one if I was just showing one, because this is important that there are many groups doing this. Having fishermen help them collect data. from the Canadian Fisheries and Science Research Society, CFRF, and the state agencies, all doing the same thing. And so one thing Cooper and I are into is gathering that data, and I'm glad to have George is more better data management than I am to do this, and gathering this all in one database and to share it and serve it and clean it and quality control it in the same way. That's important. Serve it on ERDAP. I had these mugshots on my machine. I wish I had more, but I noticed I had 12, so maybe I can make a calendar of this. Next slide. And I'm sorry, yesterday's was a little dark. I took a different angles. I couldn't get the right light, but I put them both here. Now it looks like twice as many lobstermen or fishermen there. And final one slide more. Not a big conclusion, but basically there's lots of technology is kind of change and we messed around with, but this is important to be able to talk to fishermen. I much appreciate all those fishermen that traveled there today, and hope we can keep this going. Thanks.
Thank you very much, Jim. Any questions? Looks like we've got some from online. So
yeah, I got one online here. How is the data that are gathered from the deck boxes, how do they get stored and processed?
Okay. There's Python is inside there. Little tiny brain of that Raspberry Pi is coded to, in the case of the trawls, we can't send all the raw data through the satellite, so we take an average for the trawl down the bottom. What we define the bottom is within 15% of the bottom, and we send that up along with statistics of the trawl, standard deviation, and so on, depth, and that goes into a QA/QC thing back in our desk, and then eventually we'll go into I think somebody's going to who's going to talk about this, but go into a database. And it's available online within hours or so of the haul. Numerical modelers can go there. Right now, it's a simple CSV file that modelers can grab and use them for. I think John Logan's going to talk about that tomorrow. But there's two different data sets here: non-real time and the real time. Non-real time is a little different process, but it ends up in an ERDAP. So all the many years of data on that ERDAP server, so if you can use that for, and that's why I'm happy to have George and Cooper and others and to help me with this, make sure this is up and processed and ERDAP served correctly.
All right. One more question, if anybody else. Miguel.
Hi. You said that in an experiment you measure bottom currents.
Yeah.
What's the instrument?
Instrument is something that my colleague Vitaly, is Vitaly here today? No, he was here yesterday. All it is a piece of PVC with a inclinometer on it that's tethered to the trap. And here we go. It's the same thing. Actually, these instruments that Nick makes now have tilt sensors on them. So the thing that we had Nick build was originally for these bottom current meters. Well, we realized, hey, they got temperature, wireless, we'll use those for the boat. So we ended up using the Nick's instruments for something else. But really, they're designed, and Nick has them now professionally made to very low cost current meter compared to what traditional oceanographers have used in the past. And Vitaly now, he just got NSN funded for hundreds of these off the coast. Yeah, pretty simple concept of tilting a PVC pipe. No fouling problem, not many fouling problems. Real current meters there.
So we're a little behind schedule, so Hassan, let's keep your question till lunchtime. But another round of applause for Jim, everybody. Jim is retired, but he has a hard time staying at home, which I really appreciate. So glad to have him out here. And next up, we have Dr. Alec Wang, who's the key kind of instigator for this whole workshop, and biogeochemical oceanographer. So really interested to hear what Alec has.
All right. Good morning. Welcome. Thank you for coming again. So I'm going to give a little update on sensing technology, specifically chemical sensors. So this is a kind of a little bit review and a little bit kind of development, technology development talk. So give you a sense what may come next. So this is what I think may happen on fishing fleet. So some of the parameters we think is probably ready to give it a try. So I wanted the community to know this is, I want to get some feedback as well. So how we, for example, package or design the packaging so that it fits fishing fleet operation. Let me see. All right. So I study, Glenn get a very wonderful talk on the shell fleet studies. And I study chemistry, biogeochemistry specifically, and particularly the carbon system or the carbonate system. So people may know this term, ocean acidification. I'll just give you a general overview of what that is. So people know, the CO2 increase in the atmosphere for the last 200, 300 years, okay, because we burn a lot of the carbon, fossil fuels and other activities release the CO2 to the atmosphere. And then part of that atmosphere, CO2 dissolve into the ocean, okay? So that changed the seawater chemistry quite a bit, okay? So one effect is to acidify the seawater. This is a very similar process as you carbonate your drinking water, right? You inject CO2 into water, lower pH. And the other effect is related to the fishery is we also decrease, this process also decrease carbonate ion concentration, which is the CO3 here, okay? So at least on the right are the parameters we measure, okay? As a carbon scientist, I want to know either the concentration or the value of those. So I just go quickly. So this partial pressure of CO2 is related to the how much CO2 dissolved in the ocean, right? In seawater, pH, people probably know very well. That tells you the acidity of the water, and there's the total carbonate content, okay? And there's this base, total base of the seawater. It reflects somewhat the buffering capacity of the water. And the last term is very much related to this audience, which is the calcium carbonate saturation state. Okay, so as oceans acidify, we decrease this, right? The carbonate ion content. So the total saturation state will decrease. And there's basically kind of 2-3 forms of the calcium carbonate minerals, and then aragonite and calcite. And those are the building blocks of the shellfish. Okay, for example, sea scallop, secrete the shell of it usually is, depend on the stage, but at the end is the calcite. So this value, omega, is going to affect the growth of a lot of the shellfish species. Next, please. Now, so this is Glenn, I think, mentioned quite a bit of this. So when I start this thinking, what actually the fishery-based observation can measure or can cover in terms of ocean observing. Okay, on the left, you see this spatial scales versus the temporal scales of different ocean events and processes, okay? So the square here, I kind of approximately circled what fishing activity probably can cover. Maybe, you can tell me maybe I missed something or maybe I overestimated. But my thinking is that, the ship goes out very often and can cover spatially from meters to hundreds of meters over a trip, okay? And then, if we do this consistently, like the email, then you can cover, from minutes of change of temperature all the way to decadal changes. So that's a very wide coverage. If we do this right, we probably can do, we can observe a lot of things that the normal observational network probably miss or have quite a bit difficulty to capture. So on the right, this is the model-generated variability of carbon parameters. This is the pH, acidity of it, and this is the omega. I mentioned that this is related to the calcium carbonate content in the water. So this is based on multiple years of data, and then we model it using machine learning, techniques. And then you can see, across different seasons, this is climatology. There's quite a bit spatial coverage. One problem is that so far we still have very difficult time to verify whether that's true. Okay, so I think the fishing industry can really help for us to help us to validate something like this. I think it's quite important, because if you want to project something like ocean acidification, how that's going to affect the shellfish, this kind of capability will be very critical. This is the, I mentioned this yesterday, kind of the review of what the technology available now, in the chemical sensing field. So on the left, you see there's a couple of examples. This is the DO opto. This is very much the same as Nick Lowe's opto. We did this, we developed this for freshwater deployment. But it's optical measurement, similar across many platforms. This is the optical measurement for pH sensor using optical principles. On the right, this is kind of the at that time state-of-the-art biological chemical sensors with different cost level and ready technology ready level. So the higher the number is, means the more ready. I can this probably need to update a little bit, especially the DO, because people already deploy this now. So what do we think? Develop oxygen, pH, maybe some particle measurement, transducer are ready for fishery-based deployment. So, but then the question is, what do you really want to monitor? Because we all know that we have fund or the support. We need to find the support for such deployment, and then the money always the issue. So there's a couple of stressors we think is very much relevant to this conversation. So the coastal, in general, the coastal water experience warming. As Glenn already mentioned, this part of the world has warmed pretty quick. Acidification, hypoxia, the Tracy, I mentioned that's in the Cape Cod Bay. And then there's a high nutrients issue like eutrophication, right? Specific to the Northeast, I think there's basically 4 main stressors. Ocean acidification, warming, change of circulation, which is, the intrusion of Gulf Stream, and the low oxygen, hypoxia. So those 4 stressors you can basically measure with CTDs, temperature, salinity, pH of the water, dissolved oxygen. So those basically cover those 4 main stressors in the Northeast. And this gives you some example that, how the ocean acidification and the warming may affect the growth of sea scallop. So this is the experimental results, not in situ, but when you incubate for several months of the sea scallop, the calcification rate is severely affected by the warming and the low pH water. So this will give you a summary of how that two main stressor can affect the growth of sea scalp. Next, please. So the last couple of years, we've been developing this new pH sensor. So this is target for a couple of applications. One is the mobile gears. We're going to talk about that later. And then there's also fixed, like a cage fishing gear. So to be able to capture the mobile signal, so the sensor has to be reasonably quick, right? High frequency. So that's one of the goals. And then we also want to capture the other three main stressors. So that's the dissolved oxygen, salinity and temperature. So we want to integrate the four, basic parameter sensors together, and then so that we can, with one package, then you can measure the four main stressors when you use it on fishing fleet. Please. So we've been develop the carbon and pH sensor over the last a decade. So this is the sensor we have. This is kind of so-called high-end sensor. We call it channelized optical system. So we already deployed in a couple of places. This one in the time series, this is the Pacasset River on Cape Cod. So this, you can see the high frequency temporal variability. And this is the deployment over the deep coral environment offshore of the West Florida shelf. It's about 500, 600 meters. This is the Hui dock that's out in the village. So this technology has been available for us. So and has achieved a pretty good measurement quality. So all of those measurements. So we're going to basically repackage that instrument to a lower cost package, and then adding CTD and DO to the picture. So all of those optical measurement is based on this spectrophotometric or optical pH measurement. So I don't want to go to the detail, but it's straightforward in the sense that you basically mix your sample water with the pH indicator together, and then the color of that final mixture tells you related to the pH of your sample or water. And this is very much the same principle. You use pH paper. So you drop a little water on the pH paper to change of the color, and basically it's the absorbance spectrum. We measure the spectrum and then can calculate pH. And the pros of this method is very fast, right? The color change is almost instantaneous. It's very stable, high precision. It has low pressure effects. This is important because we want to put this 100 meters below surface, and can be very relatively low cost. The con is that the disadvantage is it's still chemistry, so you need some reagent. In this case, indicator, and then you need a pump. We think we can handle this reasonably well. So that's but engineering, this is the main challenge part. So this is the prototype. So I'll say this been a new adventure for us, because we're shooting for a user not in the scientific or academic field. So the main goals here is to can achieve high frequency measurement, but in the meantime has to achieve a low maintenance. So in other words, we want the people to use it without too much of interference, right? And then can be in the water for a reasonably long period of time, and has to be low cost. So I encourage you to go to Jonathan Pfeiffer, who's my student this afternoon. So he's gonna give a show and tell of the sensor itself. And this is just a picture of it, and it's pretty small. This is the prototype at the moment. We try to package it into the in situ unit. So the question, one of the comments, one of the feedback I want to get from the community is how we package this so that you can deploy it reasonably, kind of hands-free and low maintenance. So this is the stability measurement over multiple seawater samples and tells you the standard deviation around the mean. So the standard deviation basically reflects how accurate the measurement is. And then that's on the order of third decimal pH unit. That's pretty good. I think this is good, at least for at this moment on the bench. This gives us a very good confidence, how the sensor can achieve in terms of accuracy and precision. Next. So my last slide, a little bit summary. So we think we can, fishery-based measurement can cover a wide range of the biogeochemical signals. Okay, so from meters to hundreds of meters, from minutes to decades, right? So we think that the DO and the pH sensor become increasingly available. So that's probably the next step. We want to equip it, the fishing fleet. The main stressor around the world and also in this part of the world is, acidification, low oxygen, circulation changes, warming. So we think that if we design this well, then we can capture all of them. Okay. So I tell you a little bit about the low-cost pH sensor. So far on the bench, we can achieve pretty good sampling frequency and good precision. So the next step is we want to package it. So I want to get some feedback from folks here at how we do this maybe more efficiently. And then it has to have Wi-Fi, wireless communication. And then we want to integrate it with other available sensors so that they capture the 4 main stressors. With that, thank you.
Thank you. That was great. Really quite a lot that goes into the design and engineering of a new sensor.
Yeah.
Overwhelming a little bit. Any questions from the audience? We're a little behind schedule. Linus looks like he had one.
Yeah.
Hi, Alec. Thanks for your talk. That was really interesting. I was wondering if you wouldn't mind going back a slide and kind of maybe talking through that figure where the orange and the blue. I'm curious about why those.
This one?
Yeah. I'm curious about why those. No. One more forward. Sorry. Why why those two kind of scatters kind of diverge at 9 seconds or 9 minutes or whatever that is. Thanks.
You mean this little mixture here, or this one?
The plot, the figure.
This one? Oh.
Yeah.
All right. Okay. Is that so? I didn't get into this. Obviously, this is the when we do this test, the reasonably stable temperature, which means plus minus 0.1 or 0.2 degree in the lab, and the sensor behaves very stable. That give you very stable measurement. We didn't control temperature, and then there's some warming because of the light LED we use. It warm up the water or sample. So because of that, this is temperature drift up, and then there's a pH decrease. So this is good because it actually very sensitive to the temperature change, and then this tells you that your sensor immediately responds to temperature. So this, that's what I'm saying. The high frequency measurement. This is the kind of demonstration of it.
Wonderful. Well, on that note, I'm now going to hand over the microphone to Aubrey. But can we get one final round of applause for Glenn, Jim, and Alex? Great talk. Thank you all.
All right, great. Hi, everyone. For those of you that may have joined just today, my name is Aubrey Ellerton. I work at the Commercial Fisheries Research Foundation. So the next part is going to be another panel discussion. So I'm going to invite up Rodman Sykes, Tony Alvarez, Rob, Mark Palumbo, and Doug Feeney, if you don't mind grabbing a seat up front. And I think I'm also going to try to grab a few of the model gears so that you guys might be able to describe your gear type a little bit more. So I am going to grab the pot trap. So while we're getting set up, we're going to first show a video about the longline gear, and then we'll have some of the fishermen talk about their gear types.
So we're going to share just a very brief, this is only a 1-minute clip here, describing how a bottom long line works. We don't have examples here on the tables, so we do have this sort of cute cartoon from our colleagues at Dauphin Island Sea Lab and Mississippi, Alabama Sea Grant. Thank you.
Gulf of Mexico. Our bottom long line comprises 100 hooks baited with Atlantic mackerel. These hooks are called gangins and consist of a 12-foot piece of 700-pound test monofilament, beginning with a clip and ending in a large circle hook. To set the gear, we attach buoys to one end of a reel of 1,200-pound test monofilament, the main line, and release the buoys and main line into the water. Then, we attach a heavy weight to the line to mark the beginning of the bottom long line. As our captains drive the boat forward, we clip gangins to the main line at 60-foot intervals. Once all the gangins are in the water, we attach another weight to mark the end of the bottom long line. To finish the set, we add buoys to the line and cut the line from the reel. After the long line soaks for 1 hour, it's time to haul. We pull the buoys onto the boat, reattach the long line to the main line, and start to retrieve the gear. All fishes that we can safely.
Thanks, everybody. So that's just a quick example of how a bottom long line works. And thank you.
Okay, great. All right, so I'm going to turn it over to the panelists first to just introduce themselves, give their name, their gear type, how long they've been fishing, and I'm happy to also at the same time hold up your gear so you can kind of describe a little bit. But for some of the people in the room, this may be their first experience seeing this type of gear, or particularly sensor manufacturers. So this is a chance for them to learn a little bit more about your livelihood. So Doug, if you're interested to go first, I'm happy to hold up the gill net.
Me first off.
Sure.
So I am Doug Feeney. I fish out of Chatham, Massachusetts. I've been a fisherman for 25, 26 years now. I have been a hook fisherman, and now I am a gill netter. Somewhat like this, but this is very small panels, we call it. So we set, in the dogfish fishery, we set 7-inch panels. And in the skate and monk fishery, it's anywhere between 12 and 14-inch panels. I am one of the boats that believe in stab setting, so I don't leave my gear in the water. There's no set it and forget it on my boat. I was on the square end for 15 years and saw what that did. So I've changed my fishing practices to setting the gear and hauling it an hour later and coming home with it. So that's my fishery.
Yep, and then just
Really.
about a sensor.
So the sensors that I do apply to the gear, I put them in between when we attach. So we have in a string about 15 nets, 300 feet each, and we attach them to each other right here on the bridle. And I've been putting the sensors right here. And it seemed to work very well.
Or scalloping maybe.
George actually made a housing for me. It's working quite well. It's amazing.
Yeah.
Hi, Rodman Sykes, fishing vessel Virginia Maurice, out of Point Judith. I'm a dragger, and I've been in the business since 1970. Graduated from high school in 1970. That's all I've ever done. I don't know if you've been up to look at this. Most of you are probably familiar. Same type of thing we have. We actually use a larger mesh net, but these doors go behind the boat, which spread the net, and the floats and weights open it this way.
Thank you. Yes, it spreads the net like this.
Yep. The water resistance would, they kind of like that.
Sorry, not as professional.
So the water pushes them out that way. This gets the weight on the bottom of the door, keeps it on the bottom, and the weight in the bottom of the net keeps it on the bottom. They're usually what we call ground cables between these, what we call legs and the net and the doors, and then the cables go to the boat.
Where do you like
Good.
to put the sensor?
Now, our sensors are right here on the door. On the inside of the door, encased in, the first ones we had, the small ones, were in a stainless steel pipe. And every, I think, couple of weeks, they would come down and collect these little sensors. It was like the second ones that they showed on the thing. They're just little gray things. And the technicians from the study fleet would come down and get them. The new ones are in a piece of PVC, the things that Nick made. Inside just a piece of Schedule 80 PVC, bolted to the door right in here. And we've never damaged them. They've been on there for years, and so that's a very safe place for them. We've never hurt them. So everything, that's what we do. Okay.
Yeah, go ahead.
Tony Alvarez, fishing for about 45 years, started summers with my dad ground fishing. I've been predominantly scalloping. The money was a little better, and I preferred ground fishing any day of the week, but I follow the money. Actually met Jim Manning about 30 years ago when I worked for NOAA as a skilled fisherman. So I did, research fishing, if you will, I guess, but scalloping's been my bread and butter, offshore. I don't know. What do you guys want to know about the dredge? Is that it? Or, well, anyway, the sensor, what I did on my boat was we welded a steel plate between the pressure plate and the cutting bar, drilled holes to it and bolted it on the inside to protect the sensor.
Be right in here.
Yeah.
I just don't know. Someone might not know what that plate is.
Between here and here. So pressure plate, this creates a natural suction as the dredge is being towed, water rushes in and creates a natural suction. The cutting bar will scrape the bottom, hopefully between the cutting bar and what we put chains across the mouth, depending on the bottom, but we call them ticklers. You want to tickle the scallops up off the bottom, get into that suction or what have you, and into the bag and on home.
Thank you.
Yep.
I have the truck.
Mark Palumbo, Area 3 fisherman, one of the 4 original collaborators with Jim Manning 35 years ago. I was with Joe Cote, Bob Colbert, myself. So I've been working with Jim for a long time. I've been fishing for over 50 years, lobster predominantly. My father was an inshore fisherman around Boston.
Mark, I'm sorry, this is not working. Can you just that?
This one?
Yeah, sorry. Thank you.
How about this one?
Yep.
All right.
Perfect. Thanks.
So with Jim, we've done Vemco, Tidbit. We started with some British thing that didn't really work. We've done all sorts of spreadsheets. Whatever Jim wanted, we tried. So we're now doing the Lowell with George. That has been working tremendously. George came and fixed me up with some Wi-Fi that I had on the boat. So we've had a lot of sites. Jim used to get mad at me when I would kind of move the sites around. No, you can't move those. It's got to be on the shelf. And I was like, well, I can't keep it there. The draggers are coming next week or something. But we did our best with that and got until this point where you could just move the trawls around. So we affixed now with the Lowell temperature probe, we put it in the bridge of the trap, which is basically in the middle of the trap. And depending on the time of year and the weather conditions, we probably will retrieve a trap once every week. This time of year with storms, it might be 2 weeks, 3 weeks. Now it's a great system with the Raspberry Pi, we'll send the data. We've had some problems. George just switched out. We had the satellite communicator not really working, so we would go, I would make a Wi-Fi hotspot that would get the raw data to Jim. So it's working. Whatever we're doing now is really sweet. I don't know if we want to mess with that too much because it's working. Do you want to really mess with anything that doesn't work? I don't know. But we've been all over the map with Jim. Kudos to Jim. Congratulations on your retirement. I hope you can make it work. And thank you for all that you've done for us. And I like to say the story about Jim when we had a meeting up in Portsmouth, New Hampshire, and he stood up in front of everybody and said that, well, we can't figure out if there's any correlation between catch of lobster and temperature. I was like, well, so why are we doing this? But it's been a great 35 years. Thanks, Jim.
Yeah, hello, I'm Rob Jarmel. I'm a commercial clammer out of Atlantic City, New Jersey. Been doing it for 42 years, 43 years. We started in Ocean City, Maryland. Now we're out of Atlantic City, and we have 2 boats out of Atlantic City that's got the latest and greatest design. We pull a hydraulic dredge, so it's important that we have it far enough away from the manifold that the surface water doesn't interact with it. So we put it pretty much all the way forward and up high out of the way. It kind of puts it in the way if we ever get caught in a snag of old cable or nets or something like that, but so far we haven't lost one because of that. But the information we get is pretty neat. We've gone down as far as the North Carolina line and it's close to Long Island, so we're getting some really good temperatures out of that data after the last couple of years.
The loggers that you have in your traps, are they a certain size or in a certain housing? Or?
It's basically exactly what he said, except we went for the rock block, so that records, that sends it up to the satellite, and then we have Wi-Fi at the dock to send the rest of the information up.
Yeah. And so just to kind of, I don't know if we touched on it briefly, but each of you with your different gear types, the frequency that the loggers record data can be different if it's a trawl or a tow compared to having the gear soaking for quite some time. So when the visual comes on your boat, it either has to be synthesized or summarized for an average daily temperature versus every 10 minutes. Can you just speak to your gear types for someone that may not be familiar, how long your gear might be soaking or how much data you would get in a given?
Well, our gear is down anywhere from 30 minutes to maybe an hour. And when it comes up, I mean, you can see some temperature changes. It's going down, but once it's on the bottom, it's a steady read and then comes up. As far as the frequency, I don't really know. Every 3 minutes, maybe, is it?
Thank you. Changes its sampling frequency as the depth changes. So on Rob's boats, as it's going down through the water column, it samples more frequently. And then once it stabilizes down on the bottom, it's, I think, yeah, every 3 minutes or something like that.
Thank you.
Yeah, Aubrey, I believe ours is once every hour. There is a pressure sensor on ours too that records the depth that we're set at, but you know, we're set for, it could be, you know, from, it's not, we don't usually go back and rehaul our trawls, so it's either usually 6, 8, 10 days or more.
Yeah.
So 1 hour, I believe, is enough to get with the bottom. It's pretty cool nowadays with the real-time stuff to see when the thing comes up, you know, as far as, again, trying to work with Jim and trying to understand, you know, at what temperature do lobsters become active. I was talking with Jim from Harpswell. You know, we're trying to still assimilate something with temperature and lobster catch, and I think we're getting a little bit closer now that you can see it in real time. Again, Jim will remember that we used to send these VEMCO units back, and we wouldn't get the data for, you know, 2 or 3 months, and then trying to bring that back to the day that, well, did I catch anything on that day back in September? Now just comes up and you'll see 54 degrees and you go, well, we did, you know, 100 count there, so maybe we should, you know, go over, and you go up the bank and you see that now you're at 50 degrees and you only caught 20 lobsters. It's just like, how does this really work? We're trying to get better with that, but certainly some major advancements with seeing something on a chart, and you can read the temperature, the date, and your depth. So it's, like I said, it's really going pretty good right now.
Yeah, if you don't want to just touch on like how long your gear is in the water.
Oh, well, scalping, try not to tow over an hour, but we've towed as little as 5 minutes. Why tow longer if you have a full bag? Those are sweet. We love that. I mentioned CPU, catch per unit effort. And that's what I guess every fisheries wants, you know, catch as much in as little time as possible.
We tow our net 2 hours, probably 2 hours at a time, mostly unless something happens. We're day fishing. We do that 3 to 4 times a day. So we probably have 6 to 8 hours of time on the bottom.
For the gill nets, I set them for an hour, and if I don't get my 7,500 pounds of dogs, I can throw it back in and stab set again. So the most time is I'll give it an hour in the beginning.
I guess one of the other questions, and you don't all have to answer, you can just chime in if you want to, but on the size of the sensors, I feel like, you know, Mark, you were just alluding to the Bemco mini logs. They were really small and compact. Some of them are now a foot long. Some of them are in different housings based on if they're on your trawl doors or in the trap. Do you have, if you had your ideal sensor, is there a certain size that you find is useful, or you don't care the size as long as it wirelessly talks effectively to a computer or some real time? So I just would love to hear anyone's feedback on that.
The one on it's on my port door is 1.5 foot, maybe, piece of it. Yeah, it's this thing inside of probably 1.5 inch piece PVC pipe. You put a little pin right through there to hold it in. And if anything goes wrong with it, Watson comes down and fixes it. We don't touch anything.
Here, I got a big sensor. Is this a problem for anyone's gear?
Yeah.
So, you know, small is better, but.
No, I wouldn't have, I would just bolt that onto the door, and I think it would be safe, something like that. Yeah, that'd be fine. Fine on a dredge too. According to Tony. It's good on a dredge too, right? Yeah, Tony says.
I believe that's what we have. The same thing, maybe smaller. It's in a PVC tube bolted in there somehow, and then behind a plate to protect it. We haven't fished it in the hard bottom, and I'm curious, has anyone tried this thing in the channel in the hard bottom? It'd be a lot of banging and vibration. I don't know if it damaged the sensor. So far, it's always been in soft bottom. So you want to, eventually we'll get there if you want to chance this piece of equipment.
Yeah, my preference would be what we have right now. We can zip tie it right into the bridge. It fits in really nice. I've dealt with Jim with the Vemco, the tidbit that was about this size. But we, you know, again, we've advanced with technology, and now we have Wi-Fi. It's like, oh, baby. But, you know, the Vemcos and the tidbits, you know, we've moved on. This other unit would be very difficult to, you know, secure into a trap, and it would get in the way of fishing, basically. With this little PVC tube here, it's just sweet how it just goes in there. You can zip tie it, done, you know, gets to comes up on the trap rail. There's enough distance to go to the Raspberry Pi. It's, like I said, it's working pretty good right now. I did want to mention the time that we lost a Vemco unit. Is, you know, Jim had only a few of them, and it was like, it happened to be in the one trap that I lost, and it was like, oh no, Jim. I called up Jim and said, hey, how much are those units that you gave me? He said, don't worry about it. That's all part of science. So thank you, Jim, for understanding too on losing gear.
So I just want to open it now to questions. Yep, Nick, go ahead.
Nick Lowell, Lowell Instruments. I'm just wondering, what's the minimum, maximum, and sort of typical depth you guys are fishing at? And then I really have another question for Glenn or whoever else wants to answer, like what depths are required for a good modeling and measurements. But let's start with what depths are you guys fishing at? Like, what's the minimum? Because that makes a difference in terms of, like, in some cases, turning the sensors on, and so we don't want to miss a shallow fishing event. We certainly don't want to break it because it went way too deep. And just what's sort of nominal where you guys are fishing? Because I kind of know, but I don't really know. So I'd rather hear it straight from you guys.
That's great.
Well, as far as lobster fishing, anywhere from 30 fathoms to, for me, I don't go over 120 fathoms. I know that there are some fishermen that go further east that go out to 200 fathoms. After that, I don't know if you do any work with the red crab fishermen. You know, they go out to 250, 300 fathoms. So I'm not sure if you have any red crab boats. But for us, it's between 30 and I'd say 150 fathoms.
I guess our minimum now is about 70 feet, and the max is 250.
Well, the show list has been 14 fathoms, which is very rare. Anything under 20 is generally rare. 14 fathoms right out of Boston. Boy, there was some great fishing. And the deepest was 63 fathoms, which the deeper you go with scallops, generally the yield is worse, but there are very rare exceptions. And again, probably the best fishing was in 63 fathoms, all large, 5 minutes, 10-minute tows. I got video of that, and that's some of my best.
We're usually from 10 to 65 fathoms, but 90% of what we do is between 20 and 25 fathoms.
Rodman, can you just also speak to if you have any experience with like what midwater trawl might be doing, if you have any, or any comments on that?
Not in recent years. I did some back in the 80s, but
okay.
I haven't since.
So my depths are from 10 to 30 fathom.
Any other questions? Oh, no, did you want to have the second part of your question asking for the oceanographers? Yeah, Glenn, if you want to answer that.
The edge of the continental shelf is about at 50 fathoms there. And the normal mean position of the shelf break jet there is about at 100 fathoms there. One interesting thing is that the biggest changes in both temperature and salinity are between depths of about 25 fathoms and about 75 fathoms over the continental slope. And we've actually done studies that show the spatial pattern of the warming rates. And it's actually over the continental slope, particularly just south of the south flank of Georgia's Bank, where the warming rates are the highest there. So for the continental shelf water, it would be 50 fathoms, but really catching that upper slope would probably be 150 fathoms, something like that.
Go ahead, Alex. Cooper's coming.
So as I'm thinking about the package, my pH sensor and others. Is there a weight limit? I mean, you talk about the size of it, but is there any weight limit that's gonna affect your operation? I mean, I know it's the lighter the better, but
Yep, that's a good point.
Well, it can't be real big, maybe. Yeah, well, mine's on the inside of the door. It's 10 pounds. You don't have everything that big, do you? 10 pounds.
Is that the in-water weight or is it air weight?
Oh, I don't know.
Like there are some guys that will put sensors like on their trawl on the head rope instead of like on the door, so that could impact.
Something like that on a gill net might, no?
Yeah, that works for me.
Right, yeah, this might be. I a net per se, especially a gill net, something heavy would definitely. Opposite, an auto trawl may depend as the sport. You're throwing kind of like a parachute hole. Edge is heavy-ish. Pardon the expression. That you could probably do. The problem with the dredge would be not damaging the you're bringing how fast. That's where.
Just needs to be streamlined, so it's not a big box that would make one of the trawl toys act a little different.
We did work, Jim, I don't know, probably 20 years ago, we had a salinity receiver. It was rather big. I mean, for a trap, you only have so many cubic inches to work with, so that, you know, it fit in there. You know, we had to figure it out, but, you know, we did have a salinity, we tried to get salinity data for 20 years ago. I'm sure technology and advancements that you can do something. Like I said, this is a pretty sweet advancement, something that small that can fit right into the bridge of the trap.
Did you have a question?
It wouldn't matter to us on the dredges because the dredges weigh between 20 and 30,000 pounds. So it takes something to affect it.
Can I have
Yep, go ahead.
You may not have this issue with the temperature and salinity. The ones we talk about, the dissolved oxygen and pH, I mean, we can have a reasonably robust sensor, but then there's concern, you know, from chemists, for example, when we're really interested in the bottom chemistry. You know, this is the bottom part is rarely sampled. Okay, so we really want to have some measurement, but some of the gears you're talking about are going to stir up sediment. Okay, the sensor can still, you know, measure, but that's not the actual condition of the bottom water. Is there a way we can somehow get actual bottom condition without stirring up the sediment? I mean, I guess it's very hard, but
I would
kind of
of the five people here, I think the trap is a passive fishery. It just, you know, sets down and you let it sit there for 7 days, 8 days. So, you know, once its initial fall into the water, it's basically static. And I think unless there's current, you know, towing it around, which is probably true, but whatever the bottom conditions are, I'd imagine that that's what you're recording. The other guys, I'm not going to speak for them, but they're towing a net or a dredge or what. So, like I said, it's not, there's movement there.
One of the sensors that we put on my gear, so you got to think of a gill net, and it's 12 feet high. There's a lead line holding it on the bottom, and then it's a 12-foot span. We have been attaching our sensor onto the floats, which on the top part, which holds it off of the bottom by 6 feet or so. It hangs down, so it's not getting that bottom sediment as you're talking about. So there is a way to do it on gill nets.
Just while we're on the subject, one more thought. Alec, I think that's a really interesting point. And I'm wondering, on mobile gear, if you bring it out front of, where the sediment is getting disrupted, what would be the effect? Would you be out in front of all that disturbance? I don't know, but I think we'd need to do some studies to see if that was accurate. I don't know what you guys think.
Well, on an auto trawl or a groundfish net, if you're on somewhat firm bottom and you're towing rollers, the odds are it won't stir the, you get, unless you're going to stir the rocks or the gravel or I forget, someone mentioned Cox's Ledge. I love Cox's Ledge. Nasty. It's literally a slab of rock. It's just a giant slab of rock with jagged, firm edges. and you're towing a dredge in there, and it's rock and roll, baby. Boom, 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 bang, 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 boom. You got to know how to gear up, but the fishing's great, and you tow very few rocks. So, yeah, I don't know if that. So, yeah, I think you can, on mobile gear, you can get an idea of the bottom without stirring it up, but only on certain places.
Close to the bottom do you want it to be?
No?
Question is, we want to know, for example, sea scallop. We really want to know where the seawater around the sea scallop. So this is really close to the bottom. More. We're talking about a few feet maybe off the bottom.
Well, I know occasionally, there's a lot of movement on the bottom on George's Bank where we fish, and we'll get scallops. We're fishing on scallop bottom in there. Yeah, so again, your lobster trap, like I said, that's anchored to pretty much anchored to the bottom is probably your best bet as far as if you wanted to collaborate with Tony, or you could say that's scallop bottom. I mean, I get scallops sometimes get caught up in the traps in the door or into the head, but yeah, that's exactly when they're thick, we get them in the traps.
Kind of a follow-up to what you just said, Liz Parati, Ocean Acidification Program. In comparing that information that I would get, say, from Tony and from you, what kind of proprietary issues might I come with, like where you're fishing? Can I expect that might be an issue to work with if I'm trying to pair habitat information from, say, scallops, but taking the data from lobsters?
I don't know. There's a lot of people fishing around me, so I don't think it's very proprietary. I think in today's world with VMS and AIS, I don't think there's no more secrets. Everybody knows where you're fishing.
Okay, thank you for that perspective.
Crew members. All you have to do is hire 3 crew members, and then if you have a great trip, it's probably on Facebook.
Hire older guys that are not tech savvy.
Yeah, exactly.
I think that's a good point, and it was brought up a bunch at our breakout discussions.
Yeah, you don't understand that if you tell those guys, then we're going to be fishing with 5 guys around us, and it's going to affect your paycheck because now I have to fight with 5 guys instead of just 1. So, but no, it doesn't happen. Hey, we had a great trip.
But I think along those lines, it seems, and please correct me if I'm wrong, that you're willing to share information on temperature, depth, or other oceanographic parameters. It's just when it's related to catch data that it becomes a little bit more sensitive. Is that location data? I think that, I think most guys, I mean, you guys correct me if I'm wrong, but it seems that you're okay with it. And I know many programs, they bin it by certain locations, so it's not just exact pinpoint. But you guys, if you have any thoughts on sharing your location data.
Well, you're going to have it anyways soon because this year, 2023, we have to have a locator. It's part of the agreement, and I don't know what amendment it was, that for spatial concepts that, would right whales and where we're fishing. So that has to be put on the boat this year. So you'll get, where the lobster fishermen are fishing definitely after this year.
Go ahead, Jenny.
Thanks, everybody. Jenny Ruban. I have a question. So we've talked a lot about sort of your operations in water, but I'm curious if you might be able to speak just a little bit to what your on-deck operations might look like. That might influence, sensor design, sensor type, robustness, et cetera. So how long is your gear out of the water when, you're between tows or between operations, and, how often do you put it back in? Thanks.
I've got the mic, so I'll say, usually it takes us about probably an hour to haul a 40-part trawl. So, typically the unit, the low temperature probe is out of the water for an hour, and then it goes right back in.
It takes us about no more than 5 minutes to haul, turn around and reset again. And it's probably up in the rack for no longer than a minute.
Yeah, mostly of course, the amount of wire you got to haul back, but even in 60 fathoms, I can literally haul set in 7 minutes from bottom to bottom.
So if it takes a while for a Bluetooth, that's a problem. I said, so the issue is like, if it takes a while for the Bluetooth to communicate to a screen, you're not waiting, you're going to keep setting. And that's a big thing that we hear from a lot of industries.
I catch a lot nonstop. Dredge literally will be sitting over the side in the water. So.
Yeah.
We're at 20 to 25 minutes, but by the time we start hauling the net into when we actually get it back out and towing. But the first 5 minutes is getting to the doors, which is where the sensor is. So it's probably 15 minutes that it actually sits on deck before it goes back in. And at the end of the day, it sits for 12 hours till we get out the next day. So got time.
So mine is it comes, so it gets set, stays in the water for an hour. I haul the gear, get what I need, and it comes home with me, and I do it again the next day. So I'm doing this a lot. George used the PVC to house this, and my crew hasn't broken it yet, so it worked. You know, when the gear comes up, I use a long line clip to clip it onto the float line, and I can just unclip it right at the rail, and it gets gently put in the wheelhouse. And then it gets clipped back on the next day. For skate gear, if I know the fishing is super clean and it's just skate, I might leave a string out overnight, but I'm setting this thing daily and hauling it daily.
Anyone have any other questions? Yep, go ahead.
Okay, I have an online question. Hold on one second. The other advantage to trap deployment from a biogeochemical perspective is that you capture the diel dynamics of the system instead of a simple spot reading. This was just a comment. I didn't know if anybody wanted to respond to that.
So like getting some more of the tidal variations.
Yeah, throughout a day.
I don't know if you have experience with that at all, Mark, but I know there are some lobstermen that are involved in our lobster crab fleet that, like on George's, it's pretty amazing and astounding to see the variation. But also the fact that you have a string of gear, you're only getting a logger in one trap. If you're setting on and off the bank, the temperature could be very different depending on the depth. And so is it really valuable just having one point or maybe multiple points? So if you want to speak at all, that.
Again, when we started this, it was very educational about on the bank. You know, we would set it out in 120 fathoms, and you know, I had no idea what the bottom temperature was. I mean, that was the whole point of trying to like understand, you know, why don't we catch anything in April? Well, it started to show itself when you know, we would see, you know, the bottom temperature would be 43, 44 degrees. It's like, well, okay, well, that kind of makes sense. And then as the Gulf Stream started to move in, you know, you would see your temperature on the bottom raise, which I was shocked that, you know, I think one time we got up to like 55 degrees on the bottom, you know, out, you know, on the continental shelf, which was like, okay, so the whole idea a lot of times with lobster biology is that, you know, they hibernate through the winter and then May comes along and they get a little taste of like the females that are on the bottom say, hey, it's time for me to let my eggs go. And that temperature is, you know, really important for them to start being active. And it was kind of hard to try to understand that, you know, not knowing anything. And then you see some of that stuff on the edge and all of a sudden you understand why all of a sudden you get more eggers and eggers, and then they're coming up with no eggs on them. So again, the temperature probes have really enlightened a lot as to what is actually going on down there, especially on the shelf area, which that's basically where we start. You know, lobsters like to shoal during the summer months. So, you know, that's where we start as deep as we can get, and we kind of watch the temperature come starting working up the bank.
Wanted to remind Mark, way back, say, before the time of iPads and tablets, we had this one, remember the thistle box?
Yeah, yeah.
It was a box that where fishermen can plug in and catch after each fall.
Like that box.
Yeah, we used it for about a year or two from many vessels. This is yours, Mark, from.
Yep, TA-15, yep.
Where about 52 degrees we catch here, and about 53 went up.
Yep.
Lots of good data from that thistle box, but unfortunately, the company went out of business a year later, and we quit. And while we're here, I want to notice, Mark, you remember putting the current meter on your trap?
Yep.
And back in 2011, measuring flow.
Yeah, there's something about, Jim, that 54 degrees, active lobstering, something starts happening around 53, 54 degrees that they start getting active.
Go ahead, Glenn.
In that depth range, the salinity has increased tremendously over about the last 10, 15 years. It's gone up by about 0.7 parts per thousand. And you actually mentioned salinity there. And I was just wondering, how useful would it be for you if you had salinity then, in addition to the temperature?
Yeah, well, here comes Jim, but, you know, I'm not qualified to answer that question. I'm only a dumb fisherman, but we never really, you know, we started this whole question about temperature. We didn't really address salinity. Okay, and then you hire the professional, and it's like, you know, maybe there's a little bit more to this than, you know, when you catch lobsters, it's not just temperature. Maybe there's something else. And then the brain started going with temperature, salinity, you know, but there's certainly a lot to it. So we, you know, back, I don't know, like Jim will know, but about 20 years, we threw a salinity retriever in there. So I don't know what advancements we've had with salinity and how that correlates, you know, between temperature, salinity, and catch, you know.
And one reason I asked that question is Norbert Stamps a while ago at one of the shelf fleet updates, he said, you know, it's the damnedest thing. I'm looking at these shelf fleet profiles, and they're responding more to salinity than they are to temperature. And I was really shocked to hear that. Now, normally at those kind of depths, the temperature and the salinity are varying pretty closely. But, you know, it's still an open question. I certainly would like to talk to you more about that.
Yeah, like I said, we haven't really I haven't focused a whole lot on salinity. Yes, we put a salinity retriever in there, but again, we haven't had the combination of salinity and temperature together, and then seeing catch rates with that. So, you know, we've only been doing this for 35 years.
So I just want to make sure I give a chance for anyone else. Yep, go ahead.
Well, yeah, well, if I can, I think was it you, Liz, mentioned habitat? That to me is like it's not a 4-letter word, but it's a 4-letter word. At the best, I mean, we're in a habitat, right? We're in an environment. To you scientists, especially in fisheries management or involved in the word habitat, it's criminal. It's sinful to close an area forever. And in my opinion, it was supposed to be to bring back fish. What? You're up on the edge. You're catching scallops, right? You catching any fish? Yeah. How much? Oh. Small fish. Oh, they're going into the trap for the bait. Yeah. All right. Well, I never caught fish. Hardly ever. If there was one place where you can go scallop and then not catch fish, was up on the edge, on the bank. It's been well documented over hundreds of millions of pounds of scallops have died up there. And in some cases, the bottom, I mean, some of Dave's colleagues, when he worked for SMAS, said the bottom literally turned to sponge. But anyway, let's keep an open mind when, I mean, use what word you want, but a decent rotation is the key to a successful fishery, any fishery, in my opinion. Anyway, all right.
We have about a few minutes left before we have our coffee break, so I just want to make sure to give any of the panelists any last comments that you would like to say about your fishery or sensors, if any of you do. Oh, good. Oh, go ahead, Nick. Do you have a question?
Two questions. One is a simple yes, no. Touch screens, like, love them or hate them?
Okay, if you like touch
Wet,
screens, raise your
wet
hand.
hands, gloves. But I'm thinking, so like we've always sort of wondered, like, should we even be bothering the touch screen on our devices, or like?
It's a really tough environment. We're out there. I mean, where we have most of the computers are enclosed in our wheelhouse, but still, fog and everything comes in, and you're really electronics don't like salt water or salt air environment. So your hands, I don't see it. I'd rather have the mouse, do that type of thing. And the last comment was, I just want to thank Jim for all the years of hard work. He's the guy that brought this EMO program. He's the man on steroids with the EMO program. So thank you, Jim.
Yep. We'll pass.
Hi, Jeremy Willie, I'm lobsterman out of Rockland, Maine. So the touch screen thing, I think we've come a long ways with that. And one of my units I use outside for just regular plotting, it's a MDF or MFD rather from Simrad. And I use the touch screen with my wet gloves all day. I mark both ends of all trawls all day, constantly use it for my autopilot, and it's 5 years going strong, no issues. I hate the mouse. I like having some buttons as an option for like your mark plots real quick, but the touch screen, it's honestly is pretty flawless. So.
Yeah.
A very quick observation on user interfaces, so touch screen, mouse, all that sort of stuff. Everybody's got their own opinion, and it's what you grew up with and what you're familiar with. And one of the conversations we had yesterday is essentially have headless units. So your sensors or your deck boxes or whatever have no interface on them at all, but they've got some form of communication to whatever devices the skippers and crew are accustomed to. So whether it's a mobile device, a laptop with a mouse or whatever, they can choose whatever the interface is that they're familiar with, and then it's agnostic from the point of the hardware that's getting installed on the vessel or on the sensor.
Comment.
I completely agree. That's the future. We're a long way from it, but that's where we need to go. Nick, did you have one more?
Okay. Anything else that the panelists would like to say before we wrap up?
I prefer the keyboard to the touchscreen. My hands are always cold. I come off deck. I have to do something quick. I got to try to warm my hands up. So at least, and maybe the touchscreens will get better. Probably will. But now I do much better with it. Keyboard and mouse.
I used to have like a pencil on a string next to all the electronics because, we're cutting scallops, we're turning the boat, we're constant, and I used to just grab the end of the pencil with the eraser end, up the radar, down the radar, start the track, whatever. So I owner operator, salt, especially the autopilot would drive me nuts.
It's a good idea. It's almost like a stylus that you could have. That would work.
Actually, I used to use the back of my hand. But so I was doing a turnaround till I'd just go up to the autopilot and just use the back of my hand to clean the end of the glove and spin that auto, watch it come around slowly and go back until I made my turn. Time is money.
Yeah, I think it's just a good point. Even with some of our tablets, like if there's any kind of moisture on it, it can freeze and you have to kind of turn it. Whereas I think if you use a stylus or something, when your hands are dirty or gloves, Yep. Well, if we could just give a round of applause for our panelists, I'd really appreciate your time. Thank you.
We'll get started with our first talk this afternoon. It's going to be Cooper Van Vranken and Jenny Rubin. Take it away.
Radio check. Yep. Thank you very much, George. So I'm going to kick things off with like a broader data management. Why is it important? And then, which has been kind of, a little bit our specialty and what we're contributing to, standardizing all this behind the scenes. And then Jenny's going to take over because she's the real expert in biogeochemical. This is super important and really undervalued. And we've been, like Linus and I, we've been having conversations kind of since the beginning of the week about this. And they're like, oh, this is an unsolved need. And, even beyond kind of our weird emerging ocean observation technology, this, the whole ocean observing space, fishery science, whole can of worms there as we've gotten into a little bit. But a lot of that, a lot of that could be helped with better data management. Ultimately, I think this comes down to, what is worse than having no idea what's going on? And that is that you think you know what's going on, but you're wrong. You've got these navigation things on your plane and you think you're flying clear, but you're actually flying into the side of the mountain. That's bad. So if you're putting bad data into an oceanographic model, that's worse than putting nothing in at all. So that kind of frames hopefully the importance of it. And then, an analogy of this is also, the data needs to be easily used. We got a lot of different people using data, and most oceanographers don't know anything about fishing. So the best analogy I could come up with, I often talk about food when I talk about data. I don't know why, but it's like if you were to dump the cod end on someone's kitchen table, they would say, ew, I don't know what to do with all this. They need it clean, they need it processed, they need it ready to eat, and then they're happy and they can deal with that. Maybe some of us could deal with a cod end on our kitchen table, but not normal folks. And so the key ingredients to this are the data and metadata standards. So making sure that this lines up with the other ways that other people. You can just forget that. So the data and metadata standards, this can be like making sure that you spell temperature in the same way, or the timestamp is the same as how everyone else is using it. And you'd be surprised at how common sense this is. And then metadata, so that's data about data. This is super important. That can be like your vessel ID or the type of gear that you're using to collect it. It's kind of this summary statistics about that. And the more of that you track, especially at the beginning of your data collection, even beyond what you think you're going to do, that really enables you to have a lot more kind of power with the data. And then there's a quality control test, testing to make sure you cut the bad meat off the data, something like that. So the mantra for data management is FAIR. That stands for findable. If you write something in your notebook and then it disappears at the bottom of the locker in your wheelhouse and you don't know where to find it, that's not very useful. Accessible, so this is what we're shooting for with open access data, is that you can find it and you can access it and other folks can use this data if that's what you want. This is my favorite one, interoperable. And that means that the data can be used for this, it can be used for that, it benefits science, it benefits industry, and those data and metadata standards are the key to enabling that interoperability, and even interoperability between different scientific disciplines. Final one is reusability. This, I think, speaks to a lot of problems in kind of the old way that science was done. You collect the data, you write a paper, and then it goes in the basement, and no one ever gets benefit from it again. So it's important to have that data accessible and everything else so that it can be reused and benefited again. And there's a lot of data, and there's a lot more data coming from the ocean. This is just temperature profile data. So there's more and more, and all of these data streams need to play nicely together. Same picture, whether you're talking about fishery science or anything else like that. And so how we do things at Ocean Data Network, this is a schematic of our flows. We're ingesting data both from vessels we work with ourselves or fishing industry, and then into a centralized database, putting it through a QC. So quality control, Jenny will talk more about that. And then making that accessible either directly to end users via ERDAP, the best use of US taxpayer dollars that you've probably never heard of, or putting that into other broader data aggregators so that there's these kind of like standardized pipelines for ocean modeling. But then it's really making sure that that benefits everyone. So for scientific programs, making sure that there's the traceability and the credit attributed so that everyone gets credit for the data that they collected. And then for industry, having some level of confidentiality as needed, but as we've kind of all figured out here, what's more important is that industry uses and benefits from it. So in making this presentation and trying to make it slightly exciting, I was like, oh, I'm going to show off something weird. And this is our most involved piece of data management, which is actually specifically for industry. And those red points on the bottom, that's these Moana sensors. So we're putting like 20 of these on the lead line of a seine net. So we need to track each individual position of all of these on the lead line, how many fathoms out we're doing each of those. So then what that enables us to do, just going to start? Yeah, okay, is track how the leads are falling through the water column. And everyone thinks that their seine net falls evenly, not even close. So then you can see all of these different tracks of this seine net going like that. It's still collecting valuable temperature data, so this is a win-win for everybody. Unfortunately, this is a very good performing seine net. This is the only one we got to show an example of, so you can't really see what the bad side is, but it's been a super valuable tool. Carlos is over in the UK right now doing that. So, you can do a lot the more that you track with metadata, data standards, and making sure that it goes well together. So that's the kind of key takeaway there. Hand things over to Jenny now.
Let's see, can everybody hear me? Okay. So thanks, Cooper, for the awesome first half of this talk. So I'm going to sort of switch gears a little bit and talk a little bit about quality control and quality assurance for biogeochemical sensor data. As Cooper mentioned, probably one of the worst things that you could do is have, collect a bunch of data that you think is real. So, but it's not. If there's problems with your data, if you don't have confidence that it's giving you information that is real. A good example of this, you might deploy an oxygen sensor at the bottom, on a lobster pot or on something else. But if it's poorly calibrated and maybe it's reading, that conditions are hypoxic, but it's only reading that because the calibrations are bad, you might make a decision on your fishing, or you might feed that data into a model, and it might tell you something that's completely different from reality. So having, high confidence in your biogeochemical sensor data that's going to be coming out is really important. And unfortunately, biogeochemical sensors can be quite finicky in terms of their sort of reliability for readings. The technology has gotten a lot better over time, but this is still a big hurdle for biogeochemical sensor data. So as Cooper, I guess this is a similar theme here. Data quality assurance and quality control is not super exciting, but it's super important in terms of the development of any sort of protocols or the development and implementation of any monitoring program, really whether you're talking about physical data or biogeochemical sensor data. So I'm not going to go into any of these sort of points in great detail, because what you do is going to be highly dependent on the sensor that you're using, how you're deploying it, the type of gear that it's deployed on, and what your practices are. But there are sort of 5 main themes to data quality assurance and quality control. The first is pre-deployment calibration and testing. That is a really critical piece of data quality control. So for example, your calibration at the beginning of your data or of your sensor before you put it out in the field is going to really tell you whether or not what that reading is actually, or what the environmental conditions actually are. And again, that's going to be very specific to what your sensor is, where you get it, who the manufacturer is. Some sensors are calibrated by the manufacturer. Some sensors need to be calibrated in-house. That frequency of calibration is going to be really different depending on the type of sensor that you're using. But this piece here, testing is going to be is a really important element that is sometimes forgotten before those sensors go out into the field. And I just got an image here. We've been testing a bunch of the carbon sensors that are deployed on the OOI arrays over at the Avast facility. You'll see this big yellow tank when we go there later today. But testing is really important for your sensors, because even if they are calibrated by the factory, when they come back, something might have happened in shipping, your calibrations might change. And it's really important to understand whether those sensors are reading the right values before you put them out in the field. Also, if you're talking about a distributed network of sensors across large spatial scales and also temporal scales, you want to make sure that you can compare those sensors across space. And if you don't know how well those sensors are reading in terms of the same value, you might not actually be able to compare them. Human-in-the-loop documentation is another major element of any data quality assurance and quality control plan. So taking notes about what you're seeing. When you deploy that instrument, note times about when it goes in the water, when it comes out of the water. Make notes about things like fouling. That can be really important both from your own perspective in terms of from a fisher, using that data from a fisherman, or from a scientist who might use that data at a later date to go back into that record and try to understand, okay, why do these measurements look weird in comparison to previous ones? Post-deployment calibration and testing is also critical. So pre-deployment, post-deployment. Sensors, biogeochemical sensors in particular, but others as well, are really prone to drifting over time. So how that sensor is going to respond to the environmental conditions may vary depending on how long it's been since you previously calibrated it. So if you do post-deployment calibrations, you can test and understand, quantify how different those conditions are, or that calibration is from the beginning to the end of your deployment, and actually do some corrections of your data based on that two different calibrations at the beginning and end. There are also really wonderful quality control procedures, data post-processing procedures. I'll talk about that in a little bit in just a minute. But before I move along, I just want to give a huge plug to the IUS community, the NOAA IUS community, for putting together these really amazing documents and summaries of data quality assurance and quality control for a whole host of different parameters. That's Quartad. Cooper mentioned that. Again, there's lots of resources that are available. Get rid of this so I can at least show this. There we go. And finally, the sort of gold standard in terms of checking whether or not your biogeochemical sensors are working in a region is collecting discrete samples alongside of your sensor data. This might be the most difficult type of thing to implement as part of a fishery-based observing program. But it is really the gold standard in terms of trying to understand whether or not your sensors are actually reading what the environmental conditions are. So a discrete sampling program would include essentially deploying your sensor and collecting water right where that sensor is measuring. In the coastal environment, the spatial scales, we've heard this a number of times, but the spatial scales of variability are very small. And so, you could deploy a sensor, but it doesn't really work to go, a kilometer away and collect a water sample and compare that. You really need to be right on top of the water that your sensor is also measuring. I just got some examples that you can see here. This is from the Pioneer Array, the OOI Pioneer Array, where there was discrete samples that were collected alongside the sensor. So let's see if I can show this. What you're seeing here is PCO2 in blue from one of the OOI moorings, and then our discrete samples that were collected with those deployment and recovery cruises for the OOI array, as well as salinity in purple here. And again, you've got discrete samples that are in dots on that time series. And what you can see is those match really well. And so we can feel confident that those data that are coming out of the sensor are reliable because our sensors are reading really similar values as what our sort of tried and true measurements in the laboratory are telling us. No. There we go. Okay, so digging into why we need to do this, why we need to do quality control with biogeochemical sensors. There are a whole host of problems and issues that biogeochemical sensors face. Physical sensors do as well, but as I mentioned, biogeochemical sensors are really sensitive to potential challenges in the marine environment, and they tend to be a bit more finicky, as I mentioned before. biofouling is a big issue, especially if you deploy sensors for long periods of time. So sensor deployments on short periods of time, for example, if you're doing a CTD cast with your instrument, and maybe it's only spending a short period of time in the water, probably not going to have issues with biofouling, or maybe you won't have those same issues. But sensors that are deployed for longer periods of time, for example, on a lobster pot that has a soak time of maybe a week or so, might end up with major problems. I've just got an example here to show you what this looks like. So these are dissolved oxygen data from two sensors that are deployed here in local waters. And we recovered these sensors at the time where there's this red line. And you can see this is sort of the mean oxygen concentration for one of them and mean for the other one. After we, oh, that actually got moved. We recovered it here, not sure why that happened. But when we recovered those sensors, cleaned them and recalibrated them, there was a huge step change in the mean oxygen concentration. And that's essentially because they were terribly fouled. You can see what those sensors looked like here, totally covered in tunicates, covered in algae. You can imagine that that sensor is not actually reading conditions of the sort of larger water mass around it, but it's reading what those animals and those plants are doing in the local environment right around that sensor itself. Also, you can envision having something growing on top of your sensor, sort of the sensor itself can really alter the calibration. It's not going to be reading what it did before when it was clean. So biofouling is a big issue. Drift, as I mentioned before, is also an issue. Some sensors are more plagued than others with drift. Some are more stable, and it's really going to be, again, that's sensor specific to what you might be working with. Other common problems with sensors, poor calibration. So here's a great example of poorly calibrated sensors. We've got 5 sensors all tested together before we deployed them out in the field. There's 4 of the 5 that we were working with. All of them are measuring pH, and all of them are measuring the same water mass, all at the same time in the same mesocosm. All 5 of them, well, not all 5 of them, but many of them are reading very different values. We have this one here that's reading at 8.15. We have 2 here that are reading about the same thing, and 2 here that are reading about the same thing, but different from the other 2. And so, you know, this testing, we would never have known that. We calibrated these sensors in the lab based on the recommended procedures from the manufacturer. And we, you know, if we didn't test these, we would have put them out in the field and had these sensors, you know, the spatial differences in where we were deploying them. We might attribute that to, we might attribute differences in the data to spatial differences rather than differences in the sensor calibration itself. So, of course, we went and recalibrated them, retested them, and, you know, got them to read the same value. You can do some data post-processing and corrections as well as part of this procedure. Another issue that sort of plagues some types of pH sensors and not others, and maybe some other sensors as well, is conditioning and also drying out of your sensor. Some sensors cannot go dry. They have to be kept moist at all times. And if you, I could imagine a situation where you have pH sensors potentially deployed on a fishing vessel, and they're brought up on deck and they sit out on deck for a couple of hours while you're moving between sites, and then you drop them back in the water. If that sensor dries out, you might totally alter the calibration, and you might need to have that sensor recondition before it gives you reliable data. So blowing up this period at the beginning, this sensor was not dry, but it went from fresh water as it was being stored in to seawater where it was being tested in. Blowing up that data at the beginning, you can see there's this sort of curve in the data as those pH sensors are getting conditioned to the seawater environment. They're not reading the pH of the seawater. They're not reading the right value to begin with, but they're not actually reading the proper value because it takes some time, a couple of hours, to condition to the seawater environment. You can also envision that this might be an issue if you're collecting discrete water samples as you are deploying these sensors. If that pH sensor is conditioning during that time frame while you are collecting those samples, it might not be giving you real data. All things to consider as you are sort of designing and developing sort of an observing program, and in particular thinking about fishery-based observing as well. I don't have an example of this, but for some types of sensors that might be pumped. So some sensors pump seawater across sort of the sensor itself through a tube and potentially through a mixer and across the sensor. Bubbles can be a major issue. So if you have optical-based sensors, if you have bubbles that are getting stuck in front of those optics, they're not going to be reading a reliable reliable measurement. So bubbles are also something to consider with certain sensor types. And data post-processing. This is a key piece for data quality control. and data quality assurance and data quality control. As I mentioned earlier, I just want to give a huge plug to the IUS community because there's been this very large effort over the last decade or so called QARTOD, Quality Assurance and Quality Control of Real-Time Oceanographic Data. There have been manuals that have been created by this community that exist for a whole host of biogeochemical sensors, but also physical sensors and other things, and others as well. And this includes sort of all of this information that I've kind of gone over a little bit today, recommended testing of your sensors, recommended data quality control procedures, data post-processing procedures, and examples of code that how you might implement that in your data workflow. Some of the recommendations here are automated. I mentioned earlier sort of semi-automated data processing procedures. Some of those data processing procedures you can, essentially do with no sort of local knowledge of what those environmental conditions are like. Some require some information, sort of prior information about what sort of the climatology of the area might look like. And some of those QC procedures might get better the more data that you collect from a particular area. So I think, yes, this is my last slide. And I just want to sort of give this prompt for our data discussion. We're going to go out into breakout sessions after we have a few other talks today. But to prompt for your thoughts for later, what level of involvement in this process is sort of reasonable for fishing industry members? We certainly recognize that you all are out there, you have a job to do. Your job is to catch fish. Your job is not to collect data. Maybe you might like that or think, enjoy that, but, we understand that your job is to, catch fish and, that is your business. And so, we want to make this process as easy as possible. But as I mentioned, things like discrete water samples, that's really the gold standard for being confident in our data quality for biogeochemical sensors. Is that reasonable to think that might be possible? Probably not, but it's something for you all to think about. With that, I'm going to stop. And I guess you can take any questions.
Thank you to Jenny and Cooper. We've got time for probably one question.
How would we know if the sensors we're using aren't working? They may be fouled, they may have a bubble. And if they are, what would we do to remedy that?
That is an excellent question, and I think that's something that we should all be discussing later in terms of how we implement something like this. Some of the automated QC procedures might help with that information. So if historically there's never been a really low pH event, you might flag that as potentially not real because it's never been seen before. But that doesn't mean it can't happen. For example, the Cape Cod Bay hypoxia issue, right? So these unprecedented events can happen for sure. There's some things in the data that you might expect to see that are unusual. Like I mentioned, step changes in oxygen concentration. But as Tracy mentioned yesterday, step changes might also occur from, a blob of hypoxic water moving in or moving out, and that might be really unusual. Sort of, as I mentioned, sort of the gold standard is really that discrete water sample collection that you're measuring, you're collecting that water, and you're bringing it back to the lab to measure on sort of the gold standard of instrumentation, laboratory, high precision instrumentation. It's a tough question to answer, and I think it's something that really we need to think about and should be part of the forefront of any conversation about the development of such a network going forward.
All right. Thank you both. Another round of applause for Cooper and Jenny. And I'd like to welcome Yang Chen from Stony Brook University.
Thank you, George. So thank you for invitation. And I'm the stock assessment scientist. So when you have all the data available, and the goal will be, you're going to utilize the assessment process and be incorporating into the stock assessment models. It can generate scientifically most available information to advise management. Go through the council process and so on. So what I'm going to talk about is, how we're going to utilize those environmental information in stock assessment. Let's see what. Which one? Okay, which arrow? Oh, here. Okay, thank you. So I'm going to cover two topics here. One is why environmental data should be incorporated into fisheries modeling. The other one is how we can utilize fishery-based monitoring data, because it's not very commonly used so far. But if you look at the diagram, this is basically, describe this fishery management system. You see that a lot of data will be collected, from fishery-based program, and also you look at on the top right is the environmental, ecological, and the demographic variations. Those are data you collect from the fisheries, and then you have a fishing fleet dynamics. Unfortunately, that's very hard to be incorporated into stock assessment. So the traditional stock assessment, and we only consider harvest rate and stock biomass. So we run assessment, we collect all the data, integrate them, and then we estimate what would be the fishing mortality and what would be the stock of biomass, right? And then we have a kind of what we call a biological reference point. We compare fishing mortality with a fishing mortality reference point, and we decide whether overfishing occurred. And then we also have a biological reference point for biomass, and we decide whether your population level is too low to be declared as an overfished population. And so there are the two decisions we have to make, overfishing occurred or not, or population is overfished or not. And if it's overfished, of course, you're going to kick in a rebuilding plan and all those things coming. So here you're going to see that we only consider those two things in assessment. And there's not much room for it to incorporate environmental variables. Well, we consider a little bit, but not explicitly. But we know that, the environmental change is not static, right? And so the productivity level changes over time, and you cannot set up a reference point, for example. It's always MSY, for example, BMSY, always the same. They fluctuated over time. So we have to consider that. So how are we going to build that into the decision-making process? So there's a review paper, that done like 6 years ago. It's not very updated, but you can look at it. Those authors reviewed over 2,000 stock assessment, or not 2,000, 1,200 stock assessment. They find there's only 24 of them actually incorporated the environmental variables in assessment. So you see that's really a rare case. Actually, we incorporate this environmental variables into the stock assessment and into the decision-making process. So now it's, we realize that, and we try to incorporate environmental variables in stock assessment models. So there are three ways to do that. One is you try to link the environmental very key life history processes and productivities. For example, you link that to the growth rate, link that to mortality, and those are linked outside of the model. And then you develop a relationship, incorporate that into the stock assessment model. And the other one is we can quantify how fish habitat changes over time. Like for example, a lobster. If we get involved in lobster, you don't want to compare what will happen, ecosystem for lobster in 70s, 80s, 1970s, 80s, compared with after 90s when the boom started, and they're totally different regime there. So you want to look at how the quality of the habitat changes over time. I know that Tony doesn't like a habitat, but this is we're talking about a little bit different concept here. and we also think about a survey process and also fishing process. Because change of the thermal habitat, for example, is going to change the catchability. You have a warm temperature, your lobster more active and they're moving more. So if you run the surveys, you're going to high catchability. So those are environmental variables can be linked to this the parameters that quantify the survey process and also fishing process. Okay, so that's the second way. And then alternatively, you also can use environmental variables to analyze outside the stock assessment process, but you define the time block. And they say, hey, you're within that time block, and the more or less productivity level is the same. So you have a time block, or within that time period, and the catchability is more or less same. And so you can define those time block in the stock assessment, and you're building that into the assessment. So This is forget about the details here, but this is a model that my lab developed for northern shrimp. Now, I know that northern shrimp is gone, but don't blame me for that. This model was developed after the moratorium, I think, occurred in, I think, 2016 or 2015. So this is a model that developed because, initial model, they have no consideration of temperature. And we know that northern shrimp is very sensitive to the change of thermal habitat. So what we do here is that you can look at, we built environmental factors, link that to northern shrimp growth. And we link that environmental factors to the recruitment and to the sponge stock biomass. So those are things that, if you don't include that, the sponge stock the recruitment will really solely dependent on the sponge stock biomass. But we know that that relationship will change with a different temperature regime, right? And so we're building to that, and we develop new models. And this model actually used by Atlantic State Marine Fisheries Commission. It's a kind of a base model to run their stock assessment. But that, unfortunately, that occurred after the collapse of the fishery and never recovered. So we have 2 papers published, and they test the models and look at the performance of the models, and you see that the model with the environmental variables building perform much better than the model without that. And also, we want to build environmental data into the fisheries data, actually, so that the fishery data can be utilized in stock assessment. Now, in the Northeast, unfortunately, you don't see a lot of CPUE, for example, used in stock assessment. And but CPUE, used in stock assessment in many other places, and in a lot of FMOs, for example, the tuna fisheries, and we use standardized CPUE. But you cannot use the fishery CPUE directly into stock assessment because fishermen are really good at targeting them. So you have to standardize by environmental variables, right? So that you can comparable over time and over space. And this is standardization that utilize all those environmental variables, temperature, salinity, DOs, and we all use that kind of parameters to standardize CPUE. And once you standardize CPUE, that become part of the indicator for abundance and how that changes over time. You can use that in the stock assessment. So very commonly used in a lot of tuna fisheries, pelagic species, and in other part of the world, but unfortunately very rare here in this part of the world. But we did that in the last, in a recent American Place Risk Track Stock Assessment. And Steve Cajun at University of Massachusetts, they actually developed this standardized CPUE, and they try to incorporate that into stock assessment of that. And so this is so we also want to use the environmental variables to quantify how the quality of habitat change over time and over space. So this is a kind of a typical diagram that we set up a model to quantify the habitat quality. And you look at it here is this is the data that we collect, biological data and environmental data that we collected. And from there, we try to link biological data with environmental data through static analysis to identify key drivers that actually influence abundance distribution of those fish, right? And unfortunately, in fisheries, a lot of time we don't have a catch rate. And you do have those environmental data, but you don't have a catch rate associated with it. And so unfortunately, this part, most time we actually use a survey data. But survey data has its problem because it's spatial, in terms of sampling intensity, it's relatively low, cannot afford. And there's a seasonality limitation too. Usually they have a spring and a fall, right? You don't have a lot of other season coverage. And once that model developed, the driver identified, and then you can come up with have a habitat model here developed, and then find a relationship between your abundance distributions and with each different selected environmental variables. And then you have you kind of integrate all those variables together, because habitat is not just decided by one variable, it's a group of variables. You integrate them together, and with a kind of a certain weighting scheme identified in the data analysis, you come up with a habitat map. That map, usually range from 0 to 1, with 1 as the highest quality, 0 as 0, very low quality. And this is you can do the hindcast, look back, see what happened, and then you can cross-validate it with the fisheries data, for example. Say, hey, most likely I'm going to find high CPUE here because it's a high quality of habitat. And then if you want to make a forecast, and then we have to depend on the data, environmental data, future, and then incorporate that into here and then make projections. So those are forecasting. And so unfortunately, a lot of time, fishery data will not be able to use it in that process because, we have to use the model data. So this is the kind of example that show you that the lobster habitat, the work that we have done. And you look at, this is a Pan Bay, this is the capital of lobster fisheries. And you see how that changed over time. And this is a kind of a tempo trend. So the red means that had been increased over time since 1978 to 2013. That's an early study, you can see it. And so this is that's kind of application of the environmental variable. And then we also can look at how the high quality of the habitat is changing over time. Right? You can see that from year here, and then this is the indicator, the highest quality, and then you look at how that quality changes over time, and then you can build into your stocks estimate. So this is a comparison that one without incorporate a habitat suitability index, and this one considered, and you see that the pattern is very similar, but the absolute value is different because here you look at the 1600, this is the 1200, this is spongy stock biomass. So if you use that, incorporate that HSI in the assessment model, and the model predicts that you have a higher spongy stock biomass compared with the model that without it. And so that reflects the change of a productivity here. And this is for the fish mortality, the different parameters. This is for fish, for fish mortality. And there's a season, 4 seasons. You can see that the one that with the HSI much lower than one without HSI. So that means if you build a HSI into the stocks estimate, and basically model says the population it's a better situation, better condition. And this is that we also use a habitat model and look at the productivity for American lobster fisheries, and you would define the three time period actually the productivity actually changes. And if you don't have that, we're gonna use this one, and of course it's misleading, right? You're gonna see the errors. This is the same for the productivity. This is for East Gulf of Maine, and the one before is for West Gulf of Maine. And they actually have a different responses to the change of the thermal habitat. So what we do here is that we're talking about how we can use the data in this, and what we want to propose is that we should probably use instead of a static biological reference point, we probably want to use develop environmentally adjusted biological reference point, and hopefully I think I know what you realize that, and I think that there is a research track assessment. I think we're going to talk about the dynamic reference point issues into this. So all the things that we have done so far, actually, we have to depend on because the fishery-based environmental data is very hard for us to use it because of the lack of a fish catch data. So a lot of time we have to use the model data. But we do use the fishes data actually cross-check the quality of a model data, because a lot of time when you use the model data, you're not sure about their quality. So we did my lab actually did some work on this and look at user EMO data actually to compare FVCOM data that we use to project the habitat model, and in Northwest Atlantic shelf region. So I just very quickly show you this differences. So we compare, this is a modeled, this is a EMO data, and we kind of aggregate them and do the comparisons by a certain box, aggregate data together to do the comparisons. And then just quickly show you some results. So overall, if you look at the time trend, they're pretty close, very, the correlation coefficient is very high between them over time. So we use a different measures, statistical measures, and do the comparison. So over time, yeah, they are pretty closely related. And and you plot them all. They are, you see that correlation among the E-mode in situ observations versus the model data. But if you look at this is kind of a broad spatial scale. But if you look at the specific site, so this is one site actually somewhere in here, it's a station AB01, and you see that the red one is FVCOM model data, and the E-mode is blue, and you see that they're actually very different. So fine scale, if you look at the fine scale, they're very different. And I know that, I think Jim probably can correct me, but this one is the most dynamic area, so that model, we really cannot capture the dynamics of the change of the thermal habitat there. So fine scale, not very good, but a broad scale, yes. And so the conclusion that we had for this study is that, there's a difference in terms of the performance over different seasons. And spring, fall, winter, fine, but summer got a problem with the model data. And in terms of space and high latitude, perform better, and then low latitude in terms of the model data. So yeah, I think I'll probably just stop here. Yeah. So that means that we have to think about it, So it's really complicated. I always use that to describe, how to make a decision in fisheries. There's so many different drivers there, and you try to find a way here. It's hard to get out. So I stop here. So thank you.
All right, thank you very much, Young. We only have time for one question, if there is one.
Thank you for your talk. I've heard fisheries doing stock assessments described just like counting trees, except fish are invisible and they move. What I'm hearing with this is that you're interested in using model data for the stock assessments. So is the mechanism for including the fishery observation data, would that be feeding directly stock assessments, or do you think it would be feeding and making better models that kind of that jump to including it, just thinking about including observational data into making better stock assessments?
So most traditional model, stock system model, you don't have that kind of mechanism built into the model. So if you want to incorporate specific type of environmental data that collected in the fisheries, and you need to first of all modify your current model. Okay, that one is it's not a very easy, because if you understand it, if you're familiar with the console process, it takes forever. The model changes, stock system model, they have a management track, they have a research track. Manual track, every year they have to run this because they have to set up a TAC. But for research track, that probably every 10 or 15 years, depending on the importance of fisheries. And in the management track assessment, you're not allowed to change your model. You cannot change your model. What you do is just add one more year of data, add one more year of data. You only can change your model when you have a research track assessment. Right? So that only unfortunately happens like every 10 years probably for a particular fisheries on average. And so that takes a lot of time. So one thing, but you also can, without changing the model itself, but you can modify your data. For example, if you have a survey data, we can modify survey data by linking the survey data with the environmental data. So on the West Coast, for example, survey data, we have two types of survey data. We have a design-based just added up and without considering anything. And then we have a model-based. A model-based, we actually develop models with a survey and with the environmental variables, and we built this survey abundance index. So survey abundance index already incorporating environmental variables. That happened on the West Coast, almost a lot of fisheries, but not on the East Coast, not yet. So take a long time.
All right, one more round of applause for Young. And John Wilkin from Rutgers is going to be joining us remotely. John, if you could share your screen.
Okay. I'm going to talk about, I'm a coastal physical oceanographer at Rutgers, the State University of New Jersey. And I'm going to talk to you today the talk is strictly physics. I'm going to talk about ocean circulation, temperature, and salinity. And really a short title is what we do with your data. So we've been using eMalt data for a number of years now, thanks to the efforts of Jim Manning and all of you that are acquiring the data. So I want to give you a sense of how we use it. So relatively speaking, we have a very well-observed coastal ocean globally, and yet there's still a lot we don't know about it. Observations come from the research networks and from other operational networks. We have these IOS regional associations, NERACOOS and MARICOOS, which have in the Gulf of Maine a number of moorings that deliver data in real time. At MARICOOS, we have underwater gliders. We've got surface currents measured by a network of radars. Up until just recently, the NSF was running this Pioneer Array, which I'm sure many of you are familiar with, in the Middle Atlantic Bight. And of course, we have a whole constellation of satellites that measure sea surface height, they measure waves, they measure temperature and salinity, and these observations coming from the fishing fleet. And you folks know more about how these data are acquired from the probes on different gear. I'm not an expert in that, but I love getting this data, and we do what we can with it. So those data, and so there was a question for the previous speaker about, can the data be included to make a better model? And that's exactly what we do on the physics side. We are assimilating, I'll say a bit more about that as we go on, into a three-dimensional ocean circulation model. And this is very much like numerical weather prediction. I often describe myself as a weather forecaster for the ocean. So we take all those observations and they go into a regional model here. You're seeing the domain that we cover from Halifax down to Cape Hatteras. The little green triangles are river flows. We have our daily estimates of river discharge from Water Service of Canada and the Geological Survey. And we downscale information from the Copernicus Marine Environmental Monitoring System. Some of you will know that. You may even access those forecasts from the Europeans as well. That's a global system. So what we're doing is we're adding more information in our circulation model in this region, but the cold, fresh water that comes in from the Scotian Shelf, the warm, salty water from the Gulf Stream, that's information we pull from Copernicus. We use the National Weather Service forecast, meteorology, to drive this. And as I said, we have the rivers. To be a bit more specific, these are the data services that we pull from every day. There's something like 40 programs run on our server every night to pull satellite data from the infrared sensors on polar orbiting satellites, the geostationary satellites, microwave from other sensors. We get sea level height from 6 different radar satellites, Jason Altica Cryosat. We get temperature observations from Argo profiling floats, ships, drifters, the NDBC buoys. We have our own network that measures ocean surface currents with CODAR. Some of you may be familiar with those if you're working in the Mid-Atlantic Bight. IOS and our regional associations and other groups deploy underwater gliders, 1 or 2 per month. And there's the moored buoys that I mentioned in the Gulf of Maine. And importantly here, this last item, last but not least, bottom temperature data from the Northeast fishing fleet. If we get them within 3 days, they go into our forecast system. All up about every day, I have maybe 300,000 observations of the ocean that go into informing that forecast system. Okay, so what is assimilation, data assimilation? So for any Trekkies in the room, it's nothing to do with the Borg, you will be assimilated, but it is a very nerdy, geeky thing with a lot of math. So I'm going to try and explain very quickly how it works with some diagrams. Okay, so in a nutshell, data assimilation takes a previous forecast, so like yesterday's weather forecast or yesterday's ocean forecast that I've produced. We compare it with some newly received observations. We say, it wasn't quite right. We make some adjustments to the model state so that it's a better fit to the observations, and then we generate another forecast. Generally speaking, the more data that I can get and the more diverse that data is in terms of where it's made and what platform acquires it, the more information I have, and that leads to a better analysis, meaning what do I think the state looks like now? And if I have a better estimate of what it looks like now, I get a better forecast. The model that is assimilating these data is now therefore carrying forward the memory of all of the previous data that were assimilated, and it's making a judgment about how much weight do we give to the observations. You know, they're good, but they're not everywhere. And so in the gaps between the observations, we have the model, which remembers the other observations, and it has physics in it. It's got Newton's laws of physics. It says the amount of heat that goes in must balance what comes out. So those two things together give you a better estimate of the ocean state than if you only had observations or if you only had a model. So this is how weather prediction works, and this is how our ocean prediction works. So I have something like, so we're going to simple sort of graph here, right? I've got time along my x-axis here, and the thing, sorry, hitting the wrong arrows. The thing I want to know, x, my unknown, is the state of the ocean. What do I mean by the state of the ocean? That's the temperature and the salinity and the velocity and the sea level height. And I want it in 3 dimensions, right? So I'm going to get this everywhere from Halifax to Cape Hatteras. So what I do is I've got some initial estimate of the state at time 0, right? And the black line here is I make a forecast, right? So this is today, there's tomorrow, and that's my forecast. And it's all of those variables and all the points in my model, hundreds of thousands of millions of points, actually. And then time moves on. Now we've got yesterday and today, and some observations were acquired by you folks on your ships and by the satellites and by all of our other platforms. The observations don't quite match the forecast. So I say, well, you know, if I had a better estimate of those initial conditions at the start, which I'll call X star, say, then, hey, I get a better match to the observations. So what I do is I go back and I change this estimate, produce a new analysis now, because it's not a forecast, because I'm doing it yesterday, of what the ocean state looks like. So that means when I come to today, the blue line here, the next point, is a better estimate of what the ocean looks like today because it's been informed by those observations that you acquired yesterday. And then I produce a new forecast. And then we do it all over again, right? So the trick in here is, how do we get a better estimate of that X star? And the solution, of course, is how do I do that? I use some math. Right? So there's lots of math in the system. I'm not going to inflict all of that on you. Trust me that we know what we're doing, and we're coming up with a better ocean forecast because of the model we have and the information that you're helping me feed into it. So what does it look like? I hope this is clear enough in the view. So this is just a snapshot from the oceansmap.maricus.org browser for all of our model and observation products. There's a whole bunch of layers here you can browse. And these are just showing little arrows what the velocity is every hour. If you click through on the little controls down here, you'll see the tide come in and the tide go out through Muskegon Channel and everywhere, Great South Channel. And the color here is the speed. So that's just one example of what the surface velocity looks like. That's one of the browse products here at Oceans Map. This information actually goes to the US Coast Guard. And if we just look at some statistics here of how many times an operator, an airman or someone at a SAROPS, Search and Rescue Center, or wherever accesses information, the number of requests that go to our Doppio, we call it, modeling system, we get far more hits than any other data product. So the Coast Guard really like it for velocity, surface velocity estimates. So God forbid any one of you falls overboard, but when the Coast Guard comes looking for you, they're looking at this forecast to give them some guidance on constructing their search and rescue operations. So I feel pretty good about that. But something you might be more interested in is the bottom temperature. So here is another one of the products that's in the Oceans Map site. And this is from January 15th. There's a color scale over here. It's in degrees Celsius. Sorry, we're scientists. And we can see, maybe you'll know if this makes sense or not, some relatively warm water in the middle of the New England shelf. Just to emphasize that we click through time here. This is the 19th today, and this is tomorrow's forecast for what the bottom temperature looks like in this region. Hopefully, this would match up with your experience if you are out there fishing. So just to confirm that the data is actually getting in here, I've got this little observation control panel where I can see all of the observations that went in. And what I'm selecting here is just observations that are deeper than 5 meters. So it screens out all the satellite information and things. I can see observations that were made in the water column. And this is the temperature. And we track the provenance of all of these data. So I can look at a code here that tells me where did these observations come from. And I know, because this is my system, that code 740 means it came from a sensor on one of the fishing fleets. So possibly someone in the room there. So thank you very much for those data. Other observations are coming from in situ gliders, probably operated by Hui or IUS. So we can keep a track of things. These are all the observations that came in since January 1st this year. All right. So how good is our forecast system? I'm going to sprint through this because this is a little bit sort of nerdy, but it describes the sort of assessments that we have conducted. If I look at sea level variability, so this is our model here on the left, and something that has a high correlation is good. So pale colors are good. And if something has a low error, root mean square error, again, pale colors are good. And comparing to the Copernicus Mercator model itself, GOFS, the Global Ocean Forecast System, otherwise known as HICOM, produced by the Naval Research Lab in Stennis, Mississippi, and then our model here on the right where we don't assimilate anything. And the take home lesson is our correlations are higher and our root mean square errors are lower than any of the other models. So we've taken that Copernicus Mercator information, downscaled it to this domain, added in some more data, and we're getting a better match to observations. In terms of coherence, so this is, if we've got the temperature goes up, the temperature goes down, think about wiggles in time. If things are coherent, we're matching the wiggles really well between the observations and the model. And if they're not coherent, near zero, nothing's agreeing with each other. And that's what's shown on these graphs here. And I'm just showing, for example, at some tide gauges through the Gulf of Maine and the Mid-Atlantic Bight, what we want are numbers up near 1. The Doppio analysis system is the blue line. And you can see here, we're scoring much better than all of the other models. At these very, so these are high frequencies. So this is once every 10 days. This is once every day. We've got really good agreement in the variability at high frequencies. That's because we've got a good model and a good weather forecast. And at these lower frequencies of sea level variability, we've got a good data assimilation system going into that. Now, EMALT data. So we took all of the data in the archive that we could get going back to 2007 from Northeast Fisheries Science Center, picked out the ones that had the longest time series. And here again, we've got these correlations and errors. And what you're wanting to see is pale colored dots, right? Saying that we're matching those observations. In this case, this is not the forecast system. This is our training and development of the forecast system. So these EMALT data were not assimilated in this. So it's an honest comparison as to how well does the model do when we're not even assimilating those observations from the EMALT program yet. And again, correlations are higher, errors are lower than any of the other models that we have been comparing to. I'm going to just feature one particular very long time series that goes back decades in the Gulf of Maine with this green circle here. And what we're showing here on the right is the temperature anomaly from the seasonal cycle. It's pretty easy to get the seasonal cycle right. That's not a very good test of a model. So what you want to see is how well is a model getting the month-to-month or year-to-year variability. And what we see here in this panel are the anomalies observed by this lobster trap, I assume, up here. And this is our model. And there's really good correspondence between these. We've got a correlation of almost 0.9, right? And a very small error. So we're doing pretty well with those. And something that jumps out when you look at this is the really strong warming trend in the Gulf of Maine. So what we have from this modeling system now is a map now of bottom temperatures throughout all of the Gulf of Maine, day by day by day for 15 years, that is amenable to analysis by hopefully some fisheries people, perhaps in the audience. We've got a very skillful system that is giving us information about the year-to-year variability, monthly variability, and this unmistakable warming trend that we're seeing in the Gulf of Maine. Some more comparisons. So now this is taking all of the bottom temperatures from the fishing fleet that were not assimilated, and it's a scatter diagram here, right? The models along this axis, the observations along the vertical axis. So a perfect model would have everything just lining up on the diagonal. And what I hope you sort of see visually from this is that the scatter about that one-to-one line is much less in our Doppio analysis system than in the other global models, and much less than if we don't assimilate any data at all in our own model. We also have observations from tags on sea turtles, program, I think, funded by Kudumesset Farms and others. And again, what you want to see is everything lining up on this one-to-one line. And so this is the count here. Dark is a lot of data points, and they're falling very nicely on this line. The model is not biased. The observations evidently are not biased either. And we've got not too terribly much scatter. And boy, you can really tell that these turtles like 20.5 degrees Celsius. That's almost always where you find them. So another comparison to the data. So to start wrapping things up, that's what we've done with all of your data. We have this analysis that's available, open access, anyone in fisheries that wants to look at it, 7 terabytes worth of data sitting on a server here at Rutgers. So in a summary, our Doppio forecast system downscales a global model, adds a simulation of local observations. It uses a well-configured hydrodynamic model that we've coded ourselves. We pay attention to the estuaries, to shallow coastal waters, the influence of the Gulf Stream. We've got good meteorological forcing at high resolution from the Weather Service, daily inflows of variability so that we get changes in salinity due to storms and river discharge. We've got an advanced scheme for data assimilation and a very comprehensive suite of data. I showed you comparisons of how the model performs compared to unassimilated fishing fleet data, and that's allowed us to produce this 15-year retrospective analysis that's open there to inform fisheries and ecosystem studies. The real-time system that operates every day produces a 3-day forecast every day. It does assimilate the bottom temperatures. So that's what I was showing you with those, the little dots of where the observations were and the provenance. So a big thank you, a big shout out to all of you that are involved in acquiring these data. We do use them. They are extremely useful, extremely valuable. We have very little information below the surface. We've got, gobs of data from satellites at the sea surface, but we all know how strongly stratified the Mid-Atlantic Bight Shelf gets during the summertime, and we're sailing in the dark without bottom observations. So what comes from the fleet is extremely valuable. We produce a new forecast every day. All of those outputs are available in real time every hour of the forecast from the Rutgers data server. And selected products here go to US Coast Guard for search and rescue operations information, and they're available on that Oceans Map, maricus.org website. So with that, I'll take any questions you might have.
All right. Thank you very much, John. We have time for one question.
Really nice talk. I'm Hallie from the University of Connecticut, working with Samantha Sidlecki. So I was curious if you've tried adding biogeochemistry to your forecast system, and if so, what challenges are you having and what data would you need to improve that?
Thanks. Yeah, good question, especially given the topic of this meeting. We don't assimilate any biogeochemical observations. What I described was strictly a physics model. We do have an ecosystem model, biogeochemical model, that we have run in conjunction with the Doppio physical model, but that doesn't run in operations. It could run in operations. with funding from IUS, and we've got some thoughts about how we might do that. I do have colleagues that work with us very closely at University of California, Santa Cruz. This is Chris Edwards and Andy Moore and Jerome Fetcher, and they do run an ecosystem model in conjunction with their ROMS ocean model for the California current, and they assimilate ocean chlorophyll observations from satellites, but nothing in situ. We have a research program to head in that direction, but we're not there, and we're not even really close here on the East Coast as yet. But definitely open to that opportunity and that idea if you wanted to pursue that.